Olá, bom dia a todos. Bem-vindos. É um prazer receber vocês aqui no auditório da Biblioteca Brasiliana, na Universidade de São Paulo, nesse evento que a gente preparou para vocês, a JRS Pharma, em parceria com a Faculdade de Ciências Farmacêuticas da USP. Então, tem muito assunto legal para a gente discutir hoje. Eu vou ser bem breve aqui, só dar as boas-vindas a vocês. Dizer que é super importante, a gente agradece muito a presença de vocês aqui, porque, como vocês sabem, a gente passou muito tempo sem poder fazer eventos presenciais e para a gente prepara todo esse material, todas essas apresentações com muito carinho para trazer aqui para vocês. Então, mas sem a presença de vocês aqui, nada disso é possível, nada disso acontece. Então, a gente está muito feliz que vocês vieram e estão aqui com a gente hoje. A gente vai começar aqui o evento, vou convidar aqui no palco o professor Humberto Ferraz, diretor da Faculdade de Ciências Farmacêuticas da USP. Ele vai falar aqui com vocês para a gente fazer a abertura do evento. Palmas para o professor Humberto.
Bom dia a todas e todos. Eu preciso usar máscara, né? Então eu estou usando aqui, mas aqui eu estou mais isolado, né? Bom, para mim é um prazer muito grande, pessoal, estar aqui participando dessa abertura, né? Por vários motivos, né? Primeiro porque o professor Joilson e eu, né, assumimos a direção da faculdade já faz algum tempo. E é muito importante para nós esse tipo de evento. Nós entendemos que a aproximação com o setor produtivo é algo extremamente importante e estratégico para o país, né? Durante muitos anos nós vivemos afastados, né? Universidade de um lado, empresas de outro. Essa é uma situação que não faz o menor sentido. E há, então, todo um esforço para essa aproximação. Não é muito fácil. Há queixas de ambos os lados, mas nós temos que vencer tudo isso e seguir em frente, né? Obviamente, nós não estamos vivendo o melhor momento do país, né? mas isso tem conserto. Nós vamos mudar essa realidade. E, além dessa questão, né, eu fico também muito feliz em estar aqui nesse evento, porque nós temos também o Valdomero, né, que está aí capitaneando o trabalho, e que foi nosso ex-aluno, né, uma pessoa conhecida, e sempre por aqui, né, fez o mestrado dele aqui, sempre por aqui, né, Valdomero, trazendo as coisas, conversando, né, tentando fazer essa conexão. Então, muito bacana essa oportunidade, né, e tudo isso também capitaneado aqui dentro pela professora Nádia, né, que sempre se preocupou em fazer essas conexões e buscar as empresas, né, o que não é muitas vezes fácil, mas há todo um esforço da professora também em fazer esse tipo de conexão. Como o Valdomero mencionou, ficamos muito tempo sem eventos presenciais, né, foi um momento difícil. Não que isso tenha acabado, mas pelo menos a situação está mais controlável. Nós podemos, então, voltar às aulas, aos eventos presenciais, né? E pouco a pouco vamos retomando. Lembrando, né, que o mundo nunca será mais, né, o mesmo. Várias mudanças tiveram que ser, vários ajustes tiveram que ser feitos, né? E nós incorporamos algumas dessas questões. E, obviamente, de toda essa dificuldade que passamos e ainda, né, estamos passando, há sempre boas oportunidades para a gente rever, para a gente poder repensar algumas coisas. Então, diante de toda essa tragédia, né, uma das coisas é que nós nos conectamos mais e melhor utilizando a tecnologia, né? Mas isso não dispensa os eventos presenciais, né? Eu estava comentando, né, com o pessoal da JRS, ontem eu estive no Peru sem estar no Peru, né? Então, isso é uma coisa que veio para ficar, né? Você vai sem ter ido, né? Qual que é o problema, né? O problema é que não dá para comer o ceviche, não é verdade? Nem tomar o pisco, né? E tampouco a cerveja. Então, isso é um grande problema, mas a conexão ficou mais rápida e ela toma outra dimensão nesse mundo. Mas, como eu disse, não se pode abrir mão dos eventos presenciais, a gente tem que estar sempre atento a isso. Tá? Eu acho interessante aqui, Valdomero, nós temos um bom número de pessoas, né? Geralmente, quando a gente faz os eventos, o pessoal se inscreve em grande número, na hora de aparecer, aparece um número muito menor. Isso é meio que uma tradição no Brasil, né? Mas aqui temos um número muito bom e isso é muito interessante, né? Indica aí o sucesso do evento. E uma coisa que eu gostaria de falar aqui é exatamente esta oportunidade, né? De nós nos conectarmos com as empresas e dizer para vocês que nós estamos muito empenhados em trabalhar isso na Faculdade de Ciências Farmacêuticas, né? Fora os laboratórios que nós já temos, né, como, por exemplo, o DENFAR, que tem conexões com quase todas as empresas farmacêuticas, a professora Nádia também tem um bom trabalho com empresas farmacêuticas, veterinárias e outros docentes também, né? Mas, além disso, é nossa intenção incrementar isto, né? E acaba de ser criado na Faculdade de Ciências Farmacêuticas um centro em Embrapi, que é o CENFAR. Esse centro, na verdade, ele reúne pesquisadores da Faculdade de Ciências Farmacêuticas e do ICB. E eu não sei se vocês conhecem o modelo Embrapi, mas a Embrapi, ela financia parte dos projetos e a outra parte fica a cargo das empresas e também há uma contrapartida da própria universidade. Então, os três atores se unem para poder inovar. Essa é uma grande oportunidade para as empresas farmacêuticas, tá? Para a pesquisa, para usar os resultados das pesquisas para inovação, colocar produtos e serviços no mercado. Essa aqui é a ideia. O centro ele já nasce com um número muito grande de pesquisadores e de pesquisas em andamento, mas o principal ponto das unidades Embrapi é receber demandas das empresas. Então, as empresas chegam até nós com as suas demandas e nós vamos, então, com um time de pesquisadores do centro, formatar um projeto, né? Estabelecer uma proposta para a empresa e a ideia é que nós tenhamos aí, não diria num curto espaço de tempo, porque são pesquisas de grande volume de recursos, são pesquisas muito grandes, mas em algum tempo que nós tenhamos aí produtos, né, e por que não também serviços no mercado farmacêutico oriundo deste centro, né? A Embrapi, na verdade, ela lançou um edital e foram selecionadas quatro unidades, né? 2 na USP, uma na UFMG e a outra, né, não me lembro, tá? Mas são 4 unidades e essas 4 unidades elas têm foco em indústria farmacêutica, E então nós devemos, pelo menos essa é a ideia, né, transformar a pesquisa nas unidades, né, no ICB e na Faculdade de Ciências Farmacêuticas, na medida em que nós vamos então em busca de financiamento privado para estas pesquisas, criando oportunidade também para as empresas inovarem. Tá? Mas é importante também que se diga que as empresas precisam estar preparadas, né? Precisam estar preparadas porque o volume de investimentos é razoável, tá? E elas precisam conectar essas oportunidades com as suas estratégias de negócios, porque todo mundo sabe, ao redor do mundo, as empresas fazem muita pesquisa, investem muitos recursos, mas também, boa parte dos produtos são oriundos de pesquisas em universidades. Né? Se vocês se lembram, a vacina da AstraZeneca não é da AstraZeneca, é da Universidade de Oxford. Então, tem muita coisa, né, atualmente que está no mercado e que surgiu de pesquisas em universidades, da conexão da universidade com as empresas. E também, né, as universidades também estão se reconfigurando aqui no Brasil e há muita oportunidade também para as startups, para que aquele conhecimento que foi gerado ali um trabalho de doutorado ou num pós-doutorado, que depois isso vire uma empresa e que essa empresa crie tecnologia com agilidade e depois possa ser ofertado às empresas, né? Esse foi o caminho da Pfizer com a sua vacina. Né? A BioNTech era uma startup e foi ela que criou a vacina. Então, essas conexões, elas estão mudando, né? Já mudaram, né, o cenário da indústria farmacêutica no mundo. Nós aqui no Brasil estamos um pouco atrasados com relação a isso, mas né, ainda há tempo de embarcar neste bonde. Né? Mas é preciso que nós tenhamos a exata noção de para onde estamos indo. Ou seja, é muito importante que as empresas revejam suas estratégias. Talvez poucos de vocês aqui tenham conhecimento por conta da pouca idade, né? Mas o fato é que o Brasil teve lá no passado uma grande oportunidade para a indústria farmacêutica, que foram os medicamentos, os tais similares, né? Em que você, como não tinha um sistema de patentes aqui no país, que reconhecia patentes farmacêuticas, então se poderia fazer cópia. Né? Pois bem, então essa era uma oportunidade de capitalizar as empresas e se parte desses recursos fossem utilizados em pesquisa para a inovação, nós hoje teríamos um quadro bem diferente. Mas esse dinheiro não foi usado para isso e, obviamente, a festa não é para sempre, ela acabou e as empresas não estavam preparadas para a inovação. Tampouco estavam as universidades também para ofertar oportunidades às empresas. Depois tivemos os medicamentos genéricos, também uma grande oportunidade de capitalizar, de fortalecer as empresas, mas é preciso entender que os medicamentos genéricos, eles vivem de preço. E o preço vai caindo cada dia mais. Não tem perspectiva de, com um medicamento genérico, a vida toda, né, você enriquecer uma empresa a ponto de que ela tenha recursos para poder investir em inovação. Então, é importante que as empresas entendam isso e procurem investir em inovação, com produtos inovadores, produtos que atendam, né, a necessidade do consumidor de medicamentos no Brasil e que criem oportunidades de bons negócios para as indústrias farmacêuticas. Né? E eu posso dizer para vocês com toda certeza que boa parte dessas oportunidades, elas estão nas universidades. As universidades também estão se preparando, elas querem se conectar, né? Há resistências, mas elas estão sendo vencidas, para que as universidades se conectem com as empresas. Então, os dois atores precisam entender que essa conexão ela é absolutamente indispensável no setor farmacêutico e ela precisa ser colocada em prática. Tá? E é isso que nós estamos tentando fazer, essa que é a ideia, criar, aumentar estas conexões. Por isso, todos vocês são muito bem-vindos. Por favor, levem essa mensagem para suas empresas, né? E as empresas interessadas em estabelecer essas conexões, investir em pesquisa de ponta, vocês vão encontrar aqui, né, no CENFAR e em outras partes da Universidade de São Paulo e outras universidades do Brasil, possibilidades de investimento. Essa é a palavra, investimento. Muito bem. Então, eu agradeço aqui a oportunidade que o Valdomero e que a professora Nádia me deram. Espero, desejo a vocês um excelente evento, que vocês aproveitem, né? Eu vi a programação. É uma excelente oportunidade para vocês, tecnicamente, aí, se aperfeiçoarem, né? Infelizmente, eu não posso ficar, eu tenho outro compromisso aqui na sequência, né? Mas eu já encarreguei a Michele, a Bruna e o Gustavo de depois me passarem as fofocas, certo? Gente, muito obrigado, um ótimo evento para vocês, tá bom? Obrigado.
Aproveitar aqui, agradecer o professor Humberto de novo e agradecer toda a equipe da USP, que tanto os professores, professor Joilson, professora Nádia e os alunos deles, também de pós-graduação que estão aqui, toda a equipe aí de apoio técnico também, que é super importante na realização desse evento. A gente vai dar continuidade aqui, agora eu vou chamar aqui no palco a Tereza Brose, nossa colega lá da Alemanha. Ela é responsável por toda a América Latina, pela área comercial, e ela vai falar aqui um pouco da empresa, que antes da gente começar a falar dos assuntos técnicos, dos produtos, é interessante também que vocês tenham a oportunidade de conhecer um pouquinho da empresa, onde ela está, como que ela funciona. Ela vai contar um pouquinho dessa história para vocês.
Bom dia e bem-vindos. Hello and a warm welcome also from my side. I think I have been introduced already in Portuguese. Let me just say it once again in English. I'm Teresa and I'm the sales manager working at JRS headquarters in Germany, and I'm responsible for the whole LATAM region, so I'm also supporting the local people that we have here in Brazil. So warm welcome again from my side, and thank you for taking the time and coming here. So let me just introduce shortly what JRS, the group, is doing, if it's working. So we have a very, very long history. We are a family-owned business, and we have a global network. This is like the most important thing for you, in my opinion. We see us as a solution provider and also as a system and a technology partner for you. Here I listed for you the JRS division, so you can see it's life science, where you can also see JRS pharma excipients and also coatings. But we also have other divisions such as fiber solutions and consumer products. Again, we have a global production and service network. Here you can see the different production sites and also our worldwide sales companies and our service application centers. So here you see many in Europe, but we also have the production in the US and also in India and in China. So with more than 3,500 employees and over 90 production and sales sites, we have a very good global network. We are working with many people all over the world, and this is also safety for you, and you always have someone to rely on from JRS. Again, as I said, we are also a technology and system partner for you with our R&D application centers. And you are actually really lucky, because in Brazil is one of our labs that we have over the world. Sorry. Here you can see, just for JRS Pharma now, our manufacturing network. Again, as I said, some are in the US, which is very important for you, here in the America region and Europe, but also the Chinese and India. And just to give you an idea, since we are the largest manufacturer of MCC, just to show you again, some of the plants that we have in the US are the MCC plants, which are 2 of them. Then Pharma Oy, which is in Finland, in Germany, and 2 in India, and the latest one is in China. So this was just a short introduction, just letting you know JRS Pharma is part of a big group. We are doing many different things with our fibers, and you are in good hands with our sales team here in Brazil. So thank you very much for your attention, and I hope you are looking forward to the seminar just as much as I do. Enjoy.
Would you like to put your presentation? Bom, agora a gente vai passar para a próxima fase, né, que é realmente a... Desculpa, deixar essa garrafa aqui. A gente vai começar a falar dos assuntos técnicos agora. Vou chamar aqui o Guilherme Sanches, ele é nosso colega, trabalha lá na Alemanha, e ele vai falar sobre alguns temas muito interessantes relacionados à tecnologia de fabricação de formas sólidas. Então, agora a gente vai entrar nos assuntos realmente técnicos agora. E tem novidades também que a gente preparou para apresentar para vocês dessa vez, que o Guilherme vai apresentar também. Vou deixar vocês com ele aqui. E obrigado, Guilherme. Gracias. Thank you. Guilherme trabalha na Alemanha há muito tempo, mora lá na Alemanha há muito tempo, mas ele é espanhol.
Hi, hello, and thanks for coming. The name is Guillermo. I'm working for JRS. Not really a long time. It's been a couple of years. It's going to be a couple of years in February. I'm a Spanish pharmacist by education, and after that, I jumped into the industry. So I studied in Madrid, and then I went to Germany for a short time. Came back to Madrid, and then eventually I had the opportunity to move into the excipient field because I was already in contact with that in the university, and it's something that really always interested me, and something that I really wanted to do. So I joined a different excipient manufacturer, and I was working there, always in the R&D for about 7 years or 7.5 years. I was doing mostly tablets and capsules and the usual pharmaceutical forms, and also I was really in contact with inhalation, doing dry powder inhalers. And then at some point I had the chance to join JRS, which is something I wanted to do, and I started as a product manager as well, so I was working for the high functionality excipients. We're going to talk about that today as well, and after that I joined the technical team because it's my true devotion, so to speak, and I'm currently working as a senior application scientist. We have a beautiful lab in Germany. We are able to provide with a lot of solutions for most of your problems. We are able to work very closely with all of you. We also collaborate very often with universities, and we're happy to do so and keep on doing so. I'm going to be presenting 4 things today, and the first one that we're going to explain is all the basics on cellulose, what MCC is, why do we have MCC, why are we trying to move forward with MCC derivatives, and why are those important. And I'm a bit sorry that I have to speak in English, because I can understand Portuguese pretty well, but I'm not able to speak any of it, so you'll have to cope with my English for today, and I hope it's fine. If you have any question, I'll be taking some time for that at the end of the presentation. I don't know if there is a really big, biting or urgent question, you can just shoot while I present, and I'll try to answer that. Otherwise, I'll be fully available in the pauses, in the breaks, or after that. So, good. I'm gonna talk a bit about what is the cellulose, which is It is the core of our business, and it is somehow exciting for us. And what is the future looking like, or what do we envision the future to be like? And so there we go. Let's say an SEM of some cellulose agglomerate. What is cellulose? Well, it's the most important organic compound. It's a polysaccharide. It is a fiber molecule. There's a lot of it synthesized every year. You have enough good examples here in Brazil. I believe it is a renewable source. It is, of course, insoluble in water, which is very useful for plants and other vegetables. And the goal for that in the nature is, of course, making the plant stable and really making that solid structure for the plant to grow and to be resistant against external things, wind, rain. The basic building block, if you will, is glucose. Everyone knows about this, and then that's a monomer that will be connected with others to make a chain or a chain of chains with different ramifications. So the bonds are beta 1 to 4 glycosidic bonds, and then you have a degree of polymerization of 200 bis or until 15,000 glucose monomers, and then all of those chains are bundled together, forming some microfibrils. There is some coherence between these single chains mediated by hydrogen bonds that will give the structure some sense, of course. But there is a lot of crystal defects. And then you have some crystalline forms, of course, perfectly ordinated structures with some amorphous regions that are a bit not so ordered. This is what a fiber looks like. So you have in a single fiber a number of elemental fibrils that will go into microfibrils that will, so on and so forth, build on bigger chains. And what you have is mostly crystalline regions that are intertwined with amorphous regions. So you have a gray part that is intertwined with a green one being then amorphous, and so on and so forth. And then we work with that. So we extract the cellulose, and then there is different things we can do with that, of course. And I'm going to slowly moving towards the field that is interesting for us. So starting from cellulose, you can work with that. You can just break it, you can treat it, you can do different things with it. If you only break it by mechanical fragmentation, what you have is a powder cellulose. That is our arbocell grade. So it's just basically, finely chunked cellulose. Or you can treat it both mechanically and chemically, and then you get the acid treatment with a wet mechanical fragmentation. And then you're able to take away all of those imperfect amorphous structures, and you only get the cellulose crystalline part, is what we call microcrystalline cellulose. Those are all brands, Vivapur and Cotel and some others. Good. But why is that important for us? Why is that important for the industry? Why do we use the cellulose for? Well, the cellulose is very interesting for us as a filler binder. And the reason why is because the MCC, as opposed to the powder cellulose, is really well compactable. So it's really an inert powder that works very well when you want to tablet something. You're going to be seeing this plot often today or throughout this presentation. There's a tensile strength plotted in the y-axis, and then you have a flowability in the x-axis. So of course the flowability is not only, but is mostly a function of size in this graph. The coarser something is, the better it flows. But also the coarser something is, the worse it tablets. The tensile strength at a given compaction force is how hard a tablet is, basically, and how much energy it takes for the tablet to break. And what we see is that all the powder grades, regardless of the size of it, or the angle of repose of it, or how good it flows, they are relatively low when it comes to the tensile strength. But if you take all of those amorphous regions out and you tablet those, you get up here. So the first logical step for us is, okay, let's make MCC, because if you make MCC, if you take all the amorphous regions out, then you end up with a pure macrocrystalline form that will be a very good tablet binder. And that's what we see here. But then you have different requirements in your formulation. So sometimes you need something that is coarser, something that is finer for different reasons, something that is a bit more dense or not. And that's why we have a rather complex catalog, or if you will, a number of grades that I think you've seen probably if you're aware of our portfolio. We have a lot of them. And why do we have a lot of them? Well, depending on your needs, depending on your process, in your production, you have different types. You have high bulk density, for example, low moisture. Let's say you're working with a water-sensitive API. You need something that will keep that water at bay. You have coarser grades or finer grades, depending on how the flow is, how your API is milled or not, and so on and so forth. So starting with the high density MCCs, Figure 301 and 302, you can visualize that here. 102 and 302 is pretty much the same thing. It's just the density is changing. And if you check here, you see how, of course, if you put the same weight, the volume is different because the density is much higher. So by doing that, you typically increase your powder flow. You typically improve the content uniformity when working with high density APIs. It's a very good carrier for capsule filling. And also, you're able to increase your batch weight because you're able to basically fit more in less space because the density is higher. You also have your low moisture MCCs, 103, 112, 14, and 200 XLM, depending on, of course, size and something else. So typically, you want to use those for water-sensitive APIs. So in case an API is going to decompose in the presence of water, you don't want to work with something that is, has a lot of water in it. Or for the compression of hygroscopic APIs, if the API is going to take a lot of water anyway, you need to, well, hamper that down somehow by using an excipient that is not going to take that much water. What you see here is a plot on time. So this is 0 hour, 1 hour, 2 hours, and so on. And here it jumps. This is 1 day, 2 days, 3 days, 4 days. So it's sort of like a stability study that is accelerated toward the end of the x-axis. And this is the loss on drying, which translates roughly to the amount of water that is in your powder. And what you see is that if you work with 102 in an aluminum bag, of course you keep the moisture the same because it's sealed, so there's no water coming in. If you're working with an open bag, of course at some point, past 8 hours, it's going to go up and up and up and up and up. So past 1 week, you're going to gain already this 1% moisture. But then our other things, so if you start with 101.2, which is about the same size as 102, but it's a low moisture thing, but you keep the bag open, which is this brown, I believe it's brown, I don't know how you see it, it's always a bit changing depending on you are in the room, or rather black. You see how the starting point is really low, so we are like below 1% moisture, but then if you keep the bag open, of course, depending on your lab conditions and where you are in the world, you're going to get some water intake, and then in the end you're going to reach up the same point, which is not strange because it's basically the same product that we just have produced with a lower moisture, but if you leave it, it's going to saturate at the same level, right? And of course, if you keep it in properly packed, you keep it under 1% all the time. So it's really basic, but please do not confuse what a low moisture MCC is with what an anhydrous material is, looking at other excipients like lactose or DCP. So typically this is a DVS graph. Most of you probably know a DVS, what it does is it's a dynamic vapor absorption graph. Basically what we do is we have a sample and we put it at different level of humidity, and then we check how much weight it takes basically. So starting at 0, if you put more and more water in it, it's going to take water and the weight is going to go higher. And if you dry it all the way down, you get a different curve, but you end up in the same point. And this is the important thing, because if you end up in the same point, it means that your powder did not bound any water. Now, if you would do this with an anhydrous lactose, for example, you're going to go pretty much the same way all the way up here. But when you dry, you're going to end up maybe at 2%. And that water has been integrated in the crystals in the lactose. So you retain that water and it's not lost by evaporation, it's bound in crystal water. Just to point out that microcrystalline cellulose will not bound water in new crystals. It's going to just lose it again, but of course you want to keep that under control. So. We move on to the coarser particle size MCCs, 102, SAG, 12, 14, 200, and 200 XLM. And this is just a comparison. This is how 105, the really, really fine MCC looks like. And this is how BibaPure 200 looks like. Yeah, so I think it speaks by itself. But why do you need something that is so coarse? Well, you might need it if your API is very coarse, or if your powder flow is not good enough. Typically, the coarser grades flow better than the finer grades. And you also have a dust reduction factor there. So sometimes you don't want to work with really fine things because just maybe static, everything will go and jump everywhere. So it's not really convenient sometimes. And then the final, the really fine particle size MCC, which is the 105. Why do we need something that is very fine? But sometimes you really want to put something very fine to increase the tablet binding capacity. So if you're able to, if you're lacking some tablet hardness, some tensile strength, you're able to improve that and boost that by adding 105. And this is what we see here. So, sorry, this is a particle size graph. So this is a comparison. And also for blending, so you have your BibaPure 102 here. This is your PSD here. This is 105 here, and we see how it overlaps with API. So if you want to do some sort of interactive blending, if you're not able to blend that to 105, you can to 102. Sorry, you can always use something that is a bit overlapping. It boosts the compactability in high-dose formulations. As I was explaining, this is a compactability curve of 105 versus 101. So 101 is, of course, starting at 5 and ending at 15. This is a linear, typical compactability graph, and this is how it looks like when you only do the same with 105. It's much higher, but at the same time, the cavity is that it's not flowing very well because it's extremely fine. But of course, you can mix those two up. You can make blends, and then by increasing the amount of 105, well, you're able to increase the compactability of your blend. As a summary, so we have in JRS different grades of MCC depending on your needs. If you have some formulation problems, please contact Val and the team, or maybe reach out to us if you really need that. We will be able to maybe tweak your formulation with these special grades so that you're able to tablet what you need. Flowability can be addressed by using coarse grades or high density grades. The compactability can be increased by using finer grades. And the homogeneity is a matter of matching your PSD and matching the density of your API. So you really need to take a look into what is the API I'm trying to tablet, and then how is the rest of the formulation looking like. And depending on those two factors, you can tweak your blend. Good. So we see how we move from the powder cellulose, right? Like the one that was just a mechanical mix of the breakdown MCC, cellulose, containing both amorphous and crystalline regions. How we modify that chemically to go to the only crystalline part, being the MCC grades here, with a much higher tensile strength, which is very good. But of course, it will be the beneficial will be having the best of both worlds, right? So to have something that will flow very well, so with a low angle of repose, but also at the same time we will be able to create a really high tensile strength. So we need something that tablets very well, but also flows very well. So of course for us the next step, as many of you also know, was the SMCC, and I'm going to explain a bit on how we came to that, what SMCC is, and why is it so crucial for us. So SMCC is something that we created using the Procel technology, if you will. It's a technology that we use, that we invented to create SMCC, and the way we do that is patented. But basically, you mix MCC and CSD to get a silicified version of your regular or the different kinds of MCC. And this is done as explained before. So basically you do your shredding, and this is a roll of softwood pulp, and then you chunk it, and then you do your chemical hydrolysis, and then you wash it, you filtrate it, and then you integrate the CSD, and then you disperse it in the aqueous suspension, you spray dry it, and boom, you have your SMCC here. and you have your MCC here, and you might want to say, yeah, well, they look the same, they are the same thing. They're not the same thing. They are the same thing if you look at them from afar, but if you look closer, you're going to see some differences. I'm going to go and see that later. But the important thing is that they display the same agglomerated morphological structure, and that is key because that is what drives the flow and what drives most of the properties of MCC in the first place. But then, if you zoom in, you can see how normal MCC looks like and how SMCC looks like, and now you're able to see the difference. Now you see how the surface that is relatively leak and well, pretty soft and smooth in MCC is not here anymore. Your surface is completely covered by this SMCC, by these CSD. So you have all your silica here, and there is a reason why that works so well. Yeah, so you see that in the pores, and you see that in the surface of your thing. And I believe I need to go to the computer real fast. This is a flow video, so we're trying to show you, in case you haven't been able to go hands-on in the lab and look at that for yourself. We're going to be showing how MCC flows, and then we're going to compare it on how SMCC flows. Remember, we're trying to keep the very good binding properties, and we're trying to increase the flow, as I showed before. That will be the ideal scenario, and I hope it works. It does. Good. So this is a non-direct compactable grade MCC. You see how tough it is. So we just open the gate and we try to move it around, and you see that it's just not flowing on itself. And we're going to compare it now with SMCC, and you see how you open it directly, it flows like water, and it has a perfect shape. So this is something that is designed for direct compaction. There is no need for granulation, nothing else. SMCC works as it is. It is very easy to handle, and it's almost dust-free, so it doesn't really generate. This CSD MCC is tightly integrated. It's not a physical blend, it's a co-process, and that means that it's not going to detach when you blend it, and also when you put it through a hopper. Good, and then we come to the tabletability. Good, flow is already there, but can it tablet well? Can it tablet even better than MCC? And what is the performance? And we see that SMCC is, on average, between 30 and 50% more compactable than MCC. So this is, again, your typical compactability curve. The compaction force is here depicted in the x-axis, going from 0 to 18. You might argue that 18 is too much, and I would agree with you. But this is just a proof of concept for you to know. And then in the y-axis, you have your tensile strength. So this is basically how hard your tablet is. What you want, of course, is to use low compaction forces and get high hard tablets. With MCC, with 90 or 1 or 2 grades, you get this curve in gray. And you see how much higher it gets when you use SMCC, which means that if you look at 10 kilonewton in a compaction force, you're going to reach up to, let's say, 6 more or less. So 6 megapascal in tensile strength, but you go all the way almost up to 10 when working with the corresponding SMCC grade. So there is a big advantage for SMCC there, which means that if you're looking at a borderline formulation, that you're able to make it flow and make it, go through the tablet press, but you're lacking tablet strength, or your tablets are not looking good, then you can get your problem resolved if you just switch from MCC to SMCC, for example. So coming back to the graph that we show, we have our powder cellulose in red, we have our MCC in blue, and then one step beyond, we have in orange or yellow the SMCC grades. And the same, we have different kinds of SMCC depending on the size and your requirements. We were able to put it here, again, improve flow at the same tablet hardness, and we were able to drive it higher, so increased tablet hardness at the same flow. So it's proven that silification leads to an improvement of both the compactability and the flowability of the MCC. And that is due to the higher surface area of MCC. So by doing this co-processing, by altering the surface of the MCC, we get a higher surface area. And again, we have another video, and this is self-explanatory. What you see on the left-hand side and what you see on the right-hand side is your typical B blender that you're very used to. And I think it's an iron oxide. We put basically a red colorant, and we mixed it. And it's transparent, which is very convenient for you to check how good it blends. Of course, this is not the best way of doing that scientifically, but it's a very good way of showing how it works. So we're gonna, hopefully we'll play, yeah. So SMCC is running on the left-hand side, and on the right-hand side you have your MCC. And it's gonna be a cut in the video because of course it takes some time, but you already can see how the differences are or will be. In the end, you will see that SMCC delivers with a more homogeneous blend and also a more bright or a better blend. So, of course, the revolutions are the same. This is after 10 revolutions. You might start to see already a change, which is going to become more visible the longer you blend. Of course, up to a point, MCC will also deliver a good blend, but the time is just hard. So you see how much red it is. This seems also homogeneous, but not as bright as this after 3 minutes. So, SMCC means that it promotes interactive blending and therefore content uniformity, which is of a really high importance when you're trying to work with APIs, depending on your API as well, of course, but you want to have this interactive blending going. And also, this is your blend quality. Your left-hand side is an MCC tablet, blended and tableted in the exact same way as this one, which is an MCC tablet where you can see, hopefully, some of the blue spots here and there in the surface. So you see how your API is not exactly distributed as here. So you see some spots already. Of course, if you have a white tablet, everything is going to look the same, but we try to add some color and just for you to be able to directly pinpoint where the problem might be. This will, of course, translate in content uniformity issues, which is something that no one wants. Yeah. So it's a blue pigment as model, and then you have that. Oh, by the way, this is MCC plus CSD, so we also included the CSD here to make sure that it's not the presence of CSD, but it's the co-processed, so it's the co-processing manufacturing of SMCC, so you're not going to achieve the same just by putting the silica in. Very good. So that was it for the first presentation, and I'm going to give it to Val. If you have any question before we move on, if you want to do that, sure. It's a good point. Well, that will depend, of course, on your tablet hardness and the inclusion or not a disintegrant, but we don't see a big difference, so it should be about the same as MCC. So you keep more or less the same level of disintegration time. Of course, you need to formulate it in a proper way. Thanks. Any other question? Yes? You need to start with your API, of course. So you're gonna let's say do a 30% API, and then you put typically the rest of SMCC plus your disintegrant plus your lubricant, something else if you needed some glidant, something like that. The advantage of SMCC here is, and it's a very good question, is that you are not going to need a glidant most of the times because it flows very well, so you don't need any flow aid. You can save on that. And also, you can probably go higher in API because you're increasing the tablet hardness, so you need less binding, so to speak. So you can work with less amounts of binder if you're using SMCC rather than conventional MCC. So I cannot really straight on answer your question on how much, but it could be that already a 30–40% works, particularly if you compare that with MCC. Thanks. No more questions? Good. Val?
Bom, esses pontos que o Guilherme falou, enquanto ele vai trocando a apresentação, vou fazer alguns comentários aqui. Vocês viram que esse produto, essa linha ProSolve, ela tem muitas aplicações diferentes, né? Então, a gente já conseguiu solucionar vários tipos de problema com esses produtos. Então, desde problemas de uniformidade de conteúdo, com ativos de baixa dose, ativos de alta dose também, que a gente tem dificuldade de colocar muito excipiente para corrigir esse problema. Então, pela alta eficiência em compactação do ProSolve, ele pode nos ajudar nesse tipo de tarefa também. Então, é um produto bem flexível, né? Você consegue usar tanto com ativos de baixa dose, de alta dose, resolver diferentes tipos de problema, tanto também com as celuloses especiais, a mesma coisa, né? A celulose de baixa umidade, por exemplo, para resolver problemas de estabilidade. Então, a nossa linha hoje ela conta com todos esses recipientes voltados para exatamente resolver esses problemas comuns no nosso dia a dia de desenvolvimento e produção. Agora o Guilherme vai continuar, ele vai continuar falando da evolução da celulose para um outro produto, que é o ProSolve EasyTab. A gente está combinando com ele aqui a questão das perguntas, né? Porque como a gente está com o microfone só aqui rodando, as próximas vezes que for feita uma pergunta direto da plateia, ele vai repetir para que todos possam escutar. Exatamente. E isso também dá para fazer isso, tá, Joia?
One second.
A gente tem mais um microfone extra agora para as perguntas, para que todos escutem também as perguntas que são feitas. Resolvido o problema. Obrigado.
Good. Thanks. So you really want to achieve a tablet, but you also don't want to really overpress it. So compactability is not about how hard you can press a tablet. It's about making the target hardness with the lowest compaction force possible. And this is what we're showing here. So you have different lines here, and again, this is a typical compaction force compactability profile graph. This is a spray-dried lactose. Spray-dried lactose is a very well-known excipient. It flows very well. It blends relatively well as well. But it's not really compactable, particularly not if you compare that with the likes of MCC or SMCC, of course, and EasyTab. On the other side, well, maybe before we go there, we have MDEX. MDEX is also in our portfolio. It's a spray-dried dextrate, which is working better than lactose, and it can work everywhere where lactose can, and also beyond that as well. So MDEX will be already a better alternative, but if we really go to the other extreme, so really high compactability, that will be SMCC 90, and this will be MCC, but then again, this will be EasyTab. So EasyTab is already there, really, really high, particularly higher than spray-dried lactose, and already integrates everything that you need. So already has the super disintegrant, it already has the lubricant. Oh, yeah, so it's just plotting and showing how at a given crossing force, you need to have, let's say, 20 kilonewton in compaction force to achieve that when you're working with lactose. And then you only need about 7.5 if you're working with EasyTab. Why is this relevant? Well, because the higher you press your tablets, the more stress you're putting onto your punches that also need to be maintained, and they need to be changed, and that costs some money and some energy. So it's not really nice to have the tablet at that high of a compaction force, particularly when it's not needed and you have other options. We have a lot of application studies. I'm going to be presenting a lot of things, which is very nice, and I hope it's interesting, but please bear with me a bit. This is a study for probiotic tablets. Maybe some of you are working in that field. A probiotic tablet is basically a mixture of living organisms with something that you put into a tablet, a granule, a capsule, something like that. And what you want, of course, is that those living organisms to actually go into your body alive, which seems very self-explanatory, but when you think of it, you're putting living organisms in a tablet and you're pressing the powder together. So just by mechanical shear force, you're crushing some of them, and you're going to be, killing them, and they won't be able to do what they need to do in your body. So what you want to do, this is starting with bifidobacterium, and you want to have the most cell count possible after the tablet. And we see here in a graph how if you increase the compaction force, of course, too much, you're going to kill all of your bacteria to the point that only 10% of them will survive if you really go to that point. There is another number of challenges with this formulation. Of course, not only this, but the stickiness of the sticky nature of living organisms. And then really, if you have to compress something, if you want to keep, let's say, no less than 90% of the bacteria alive, you need to work at maybe 7 kilonewton, something around those lines. So you need to have something that tablets well enough so that you can get already a tablet with a low compaction force, and that is EasyTab. So what we did is we compared EasyTab with spray-dried lactose. Spray-dried lactose is, of course, nothing you want to use most of the times in one of these formulations because it's not really neutral-friendly for a number of reasons, mostly clean label and so on. But EasyTab is really the solution for this, and you see, you only need 9.8 compaction force for achieving an 80 Newton crossing strength tablet. So for achieving a not so hard tablet, a tablet that is decently a tablet, you need only 9.4 in the case of EasyTab, and you need to go all the way to 30.5 when using spray-dried lactose. But then the problem is the survival rate. You see that if you use that, you're going to kill 40-some% of your bacteria in the lactose formulation, and if you keep below 10, you're going to have a 91.5 survival rate. So it's really an advantage to use EasyTab for these formulations. And this is a bit why and how it works. So because of the porous structure of a tablet done with EasyTab, you still have some room for the tablet for the bacteria to sit in and to survive. And this is how it looks like when you press to 30 kilonewton a lactose formulation. So it's basically, there's no room for anything and the bacteria is crushed and dead. Homogeneity. Yeah, so we're gonna see a number of slides that was done by the university in collaboration with us. Some of these slides are just to show that there is no big difference, and some of them are going to undermine what is the actual importance of EasyTab. So we compared a process of EasyTab SP with atenolol formulation, and then just a physical blend of the ingredients, so SMCC with the super disintegrant, with the lubricant, and the API all together. And then we check that in the image, and it's basically, okay, you might argue that you see more here than here. The blue will be atenolol. Not really a big difference. We move on. And then we look at the particle size distribution. You probably cannot even see the number from there, just trust me. It's pretty much the same, so you have a different distribution maybe, but both blends will flow. So also not a difference from the physical blend. So yeah, you start to question what is actually the difference. And this is how the formulation looked like. So this is in blue our formulation 1 using EasyTab SP, and this is formulation 2, which is just a physical blend, a dry blend of the excipients. So of course, what you see here in the EasyTab and what you see here is different because they are different components, but the amount that you will get is basically the same in both sides. So this is just to show you how it looks like. Then this is where we're going to start seeing the differences. So first of all, we look at the compactability. The compactability is already higher when you use EasyTab compared to the dry blend. So you see already how at the same compaction force as, let's say, 6, you have already like almost 1 megapascal more harder tablets. They disintegrate also faster. So this is the disintegration time in seconds at the same tensile strength. So if you, let's say, if you go to 3, you're going to have 20 more seconds in the dry blend. So they're going to be less hard. They're going to take longer to disintegrate. The ejection force, because of how the lubricant works and how the lubricant is distributed in the formulation, is going to be extremely high compared to the one of EasyTab. Do you want to have a lower ejection force? Ejection force typically relates to how well your tablet is lubricated. So when you eject the tablet from the die in the tableting press, you can monitor your ejection force. And we see how you want to keep it as low as possible for keeping your tooling in a good shape. And then we have an equivalent dissolution profile. So it doesn't really make any difference when we go to the dissolution profile, but it does in everything that has to do with the process of the tableting itself and also of your tool conservation, which is eventually also going to cost you some money and some hurdles, and is something you really want to avoid. But maybe the most important thing is the content uniformity. So of course you want to have your content uniformity throughout your tablets, and you want to keep it as tight as you want. So you want to match the label of the formulation, and you want to keep it as close to that 100% as you can. And what we see here is that the content uniformity is 0.74% in difference from tablet to tablet, where we have a 7.93 in the dry blend. So it's not blending that well, or maybe it's blending that well, but if you put that in a hopper and you tablet it, it's going to degrade in the hopper. So it's going to, through the vibration, it's going to detach from one another, and you're going to have this problem in the end. So the main challenge is the content uniformity. It's not the disintegration. You might be able to overcome some of the tableting properties by tweaking with your equipment, but this is something that is really making a difference. So we have a 10 times higher content uniformity when using EasyTab. We have an improved tablet hardness and a better weight uniformity. We don't have any over-lubrication. Over-lubrication is very important. Typically, you need to lubricate your blends. If you don't lubricate your blends, your blend is going to stick to the punches of your tableting press, and then you're going to keep on having problems with content uniformity, with the weight uniformity, with your tooling as well. So you want to lubricate it, but you also don't want to lubricate it typically too much, because if you over-lubricate it, then the lubricant is going to go everywhere in your formulation, and you're going to lose a lot of binding effect. So if you overdo it, you're going to have a classical but dramatic decrease in compaction force and, in tablet hardness. So this is a typical physical blend with magnesium stearate. Magnesium stearate, the very well-known lubricant that pretty much everyone is using. I'm going to be presenting something different today, but let's take magnesium stearate. If you overdo it, you see how it plummets. So within a difference of, let's say, 10 minutes in blending time, just goes down. And of course, the solution say, well, I'll just blend for 2 minutes. And if I blend for 2 minutes, I'm going to stay here in this range. Yes, but then you're going to put your blend into a tablet press that has a hopper that vibrates and that moves. So you're going to keep on. The blending doesn't stop the moment you stop the blender. The blending of the blend is going to continue through your process. If you transport the blend, if you tablet the blend, you're going to have some differences. And everything is going to add, and the crushing force is going to drop. So if you're having some problems with your crushing strength, and you're lubricating, and you think that you're over-lubricating, this is really something to look at. If we do the physical blend with proof, and I don't want to deep dive into proof because I'm going to explain it after the break. If you do it with proof instead of with magnesium stearate, you can keep it at bay for quite some time, or at least longer than you can with magnesium stearate. But if you do it in the most elegant option, which is easy tap, you see no over lubrication at all. So you're able to do it and transport it and blend it and put it in a hopper and vibrate through it, and you're going to keep that level of tablet hardness. So you mitigate those time effects. Sometimes it's about mitigation. Sometimes it's not that you're just blending wrong, or that sometimes you cannot avoid this overblending. Sometimes because of how your process is designed, you're going to have, to some extent, some overblending, and you want to minimize that, and we have a very good option here. We did a study with hydrochlorothiazide, HCT, again, your easy tap formulation versus your physical blend, just to show that those are the quantities that are going in, both are the same. And this is how it looks like. So this is the dissolve active in time, and this is where you use the dry blend, and this is where you use easy tap, and you see how tight it is. And of course, the lubrication, depending on the lubricant that you're using, is typically something that's hydrophobic. So putting too much of a lubricant also affects how your dissolution profile is going to look like. So you also don't want to overdo it for this reason. If you use a dry blend, you see it goes all over the place. If you use easy tap SP, it's much more tight. So you have highly reproducible dissolution results with easy tap. Very important for coating, your smooth tablet surfaces. I believe Rudy will show some tablets later. Those were pressed with easy tap. Of course, it's not the goal is going to be to display the coating, but keep in mind that those tablets were pressed with easy tap. It achieves a very, very good thickness to the tablet of the coating of the coating to the tablet. Also with the embossing, they look fantastic, but you'll be able to look at that later. So, and the final point, I believe, is the rapid disintegration of it. And I'm going to play a video, but before I do that, bear in mind this is just the tablet in water. It is not stirred, it is nothing, and it's real time. So what you're going to see is how we put a tablet that was pressed with easy tap into a beaker with water, just with water, and how is it going to open up and disintegrate. And of course, this is not going to be your real dissolution thing, and of course, this is not how you should do it, but this is, again, just a this display on how fast it really takes up the water and breaks apart. We're talking really seconds here. And I believe, yeah, so already 24 seconds, the tablet is completely broken. And I think we're going to prove it by moving it a bit. It's completely gone. And we're going to go to the final part of the presentation, and then we're going to have a break. But I'm particularly happy about this part. This is a work that we were doing with the University of Eastern Finland. Continuous manufacturing is, we believe, the future. We see that moving forward, not only in Europe, but in every other place. Not everyone is ready to do that. Back before the pandemic started, we would go to seminars and people would talk about, yeah, we're looking into continuous manufacturing. We believe in the beginning of maybe 3-4 years, we're going to be switching to that. And people were saying, yeah, maybe 10% of the companies will switch to continuous manufacturing, but the rest is going to remain into the traditional manufacturing. And now we see how everything is flipping over. We attended a seminar of FETA, the tablet machine, and then we're discussing, of course, continuous lines. And they estimate 80% of the people in, say, 10 years is going to switch into some degree to a continuous manufacturing line. So we believe it's the future. We believe it's going to be taking over the industry. And this it's not new, so to speak. So people has been playing with the idea for quite some time, but there are already some companies producing continuous manufacturing. There are already some products manufactured in continuous manufacturing lines. And there's a number of advantages. And I think we have a bit of an explanation here that I'm going to just show to you so you're able to understand the concept, which is very simple, if you don't know already about it. So this is how your typical batch manufacturing process looks like, with differences, of course, from process to process, API to API. You have your synthesis of your API. You typically synthesize a batch. You test it. You store it. If it's good, you release it or not. You crystallize it, blah, blah, blah. And then let's say you're able to do that with each and every one of your components. We're talking API, we're talking super disintegrant, binder, lubricant, with everything you have. So you have a lot of different suppliers. Each one is doing their own thing. In the current scenario of shipping and prices and stuff, it's also not something you want to have. A lot of different people where you have a lot of different points in which something can go wrong. And then you have all the ingredients in your storage, and then it's all right, can start. So I need to do blending, and then you just have, let's say, a small blender. You have a 200 kilo blender. I don't know, just an example. And then you blend, and then you test. And if it's good, then you can move on. You have to maybe store it for a bit or not. And then you move into your granulation step if you have to granulate, if you haven't switched already to a direct compaction line. And then you granulate, and then you have to sieve, and then you have to test, and if everything is fine, you move forward. If something is not fine, you need to start over. And then you tablet press, and then you coat, and then you blister, and so on and so forth. So there is a lot of silos that you have to tick before you move on to the next one, the next one, the next one. This is the traditional process. This is how everything has been going. And what continuous manufacturing, what the idea behind continuous manufacturing is that we're going to move on from that into something that is not batch-based, but continuous. That is streamlined in a way that everything will move in the same line without actually having to separate the productions based on the capacity of the blender and the tablet press and so on and so forth. And then those intermediate steps of release testing, those will be done by PAT, so process analytical techniques, everything that is done inline. Basically, you're going to start up, ramp up your process, and then your process will be running. And then you have a couple of sensors or a couple of places where you can just test. And at some point, it's going to start up, not going to be in spec, not going to be in spec. And at some point, it's going to reach this so-called steady state where you're able to run your line and everything will work. And then you're able to test. And if the testing in between is fine, you know that your quality of your product is going to be fine. So you're going to be eventually reducing your testing time. You're going to reduce your storage. And you're going to reduce a number of things. So it is not only better from the quality perspective, but it's also better for the manufacturers. And the reason why we believe this is the future is not because we think it's a cool, nice idea to do, which we also do, but it's because the authorities are looking at this as, all right, so now the only way for you to keep running a line like this is to make sure that the quality of the process and the products is good enough. And the authorities are typically only worried about the quality of the final product. So they say, okay, so if you have an incentive to keep the quality up so that your line will run, then we're happy to have this process, and we're going to make things easier for you to run this process, because in the end, the quality of your tablets is going to be better. So that's why we see this scenario moving, because the authorities are looking into it and saying, we need this because it's going to increase the quality and it's going to be better for the end consumer, for the patient. And that's one of the big reasons. And of course, on the industry side, there is a lot of options to reduce the number of tests, reduce the number of storage, and there is a lot of logistic nonsense that will be cut off. Good. Well, I explained pretty much all of this in what I said. Smaller equipment, more flexible footprint. You're going to be able to produce in smaller spaces with no storage in between. You're not going to scale up, so you're going to do your development and your let's say development batches if you want in the continuous line already. And once you know how it works, you can run it for basically as long as you want. So the batch size is not going to be depending anymore on how big your blender or your granulator is, but on how long you want to operate this thing and at which speed can you run the line, right? Most of the time, it's going to be steady state production. How long? I really don't know. So basically, once you ramp up and you make sure that you hit the steady state, you can keep on running with this process for long and everything will be fine. You're going to automate a lot your line, so you're going to have less people working there. You're going to minimize the amount of problems that you can have in the production process, and you're going to diminish the workload, so the people doing that instead can be doing something else. You can have a real-time quality control that will, as I said before, hopefully increase the quality standards of the final product. And you're gonna need, it's not a result, it's a tool basically. You need to understand your process much better to run it properly. And then you'll be running a closed system, so there's gonna be less chance for contamination. You don't need to take the blend, open it up, pump it in some other place. So there is a lot of advantages, of course, to this kind of thing. So there is a number of challenges as well. It's not going to be easy, and everyone is trying to figure those out. So how do you start up the equipment? How long does it take to reach the steady state? It's not clear. It's difficult. That was unexpected. Sorry about that. Yeah, it's... Anyway, another big question is, where do you put your eyes in the process? So where do you test? You know, we're saying that we need to look into different points in your process, but is it after the blending step? Is it after the tableting step? Do we do it before? Do we do it after? So everyone will do it, I believe, in a different way, and this is something that the companies and the equipment manufacturers have to find out by themselves. We need to find the right process control strategies for pharmaceutical applications. It will change from a granule, from a capsule to a tablet to an injectable to something else. It's going to change by the nature of the product. And this is where we play a role, and this is why I'm here telling you all of these things. We're not ready yet, most of us in the API manufacturing, but particularly in the excipient industry, we're not ready yet, we are, but some other people are not, to jump to continuous production, particularly not for continuous feeding. So you cannot run a new process with an old excipient most of the time. Some things you can, sometimes you can adapt something, but you're going to need something that is designed for a line that's going to be running for longer in a different way. So looking at the process, and this is basically in a scheme of how a continuous processing line is going to work like. This is your feeder, so you have 3 hoppers, you see, and then you have a mixer here, and a conveyor for powder will put it all the way up, and then you have your tableting step, and then blah, blah, and so on and so forth. The main problem for us are the feeders, because you need to put the powder somewhere. Not the main one, but one of the big ones is powder flow. Powder has to be flowing well enough, because once you close the system, you need to trust that it's going to move on. Content uniformity is going to be a big role. There's a number of things, lubrication. But the first one that we have is feeding. So powder feeding and powder blending is key when it comes to excipient. You need to have those under control, otherwise your process is not gonna work. So of course, we try to study this, and we try to look into, all right, let's see what the individual excipients do. Let's see what EasyTap does in a state of the line at the time, continuous manufacturing facility. And we're going to check the fitting performance, and they want to see how is the mixing speed altering or not the particle size distribution of the powder. We're going to see how the continuous DC So how can you compress it in the end? Because it doesn't really matter how good can you feed it or how good your particle size, your blending is, and in the end you need to keep having a tablet, and if that doesn't work, then nothing that we do matters. Huh? So the first thing is powder feeding. So powder feeding is influenced by basically two things: the feeder design. So mechanically, each manufacturer will do that in a different way. You have different powder feeding systems, and of course the powder properties. So both what you put in and what is it that you put that in. You need an accurate powder feeding, of course, to keep a content uniformity in place. It's not big news. Huh? We have in the study 3 different feeders because depending on what is it that we're going to feed in the line, we're going to need a different feeder because the feeder will adapt to whatever it is that you put inside, right? So we have a standard large feeder with a load capacity of 20 kilo, rather big. We have a granule feeder with a smaller capacity, and we have an even smaller modified feeder with a loading capacity of 3 to 4 kilo. And what I'm going to be showing now is how we cope with the individual components versus how the EasyTab perform, right? So again, the question here is, fair enough, EasyTab works, but would the individual components work just as well? Or are we going to have, what is the continuous manufacturing, or what is the co-processing do for continuous manufacturing? And that's why the importance of EasyTab is not that includes all of those things, but the fact that we achieve that into a single component. So this is how the study looks like. Basically, you have your all-in-one EasyTab, and then you have your individual ones. So basically, MCC, the silicon part of the MCC, your sodium sarglycolate, your disintegrant, and your SSF, so your lubricant. And then depending on the size and the particle shape and the flow, you're going to use one or the other feeder. So we have a large feeder, a granule feeder, and then for the really, really bad flowing fine stuff, we're going to use a different feeder. Good. It's going to be a lot of graphs now. But I'm going to try to explain. We don't have to really go deep in this. We have a mass flow here on the y-axis, sorry about that, and we have time. So this is how much it varies, how much jumps up and down the mass flow, so how much weight goes per hour into the system at different feed rates. So this is slower and this is faster speed. So you sometimes, let's see how much we can push it. What you want to have, of course, is a stable mass flow through time. So you want that it flows like water continuously, right? That's the ideal situation. What we see here is that it's not happening. And this is the mass flow, and this is the same for each feed rate here in the bottom at motor speed. So basically, how much effort does the machine have to make to keep the flow running? So we see that basically high motor speed and an absolute mess. This corrects a bit when we go a bit higher in feed rate at the price of also 5 times the motor speed. And then when we bring it even up, we have the motor speed here, but then we start to see again how it goes up and down. So you can feed it, but it's not that stable. If you use a different feeder, and if you use a smaller feed rate, like a lower feed rate, you can keep a very decent mass flow. It flows well. MCC by default doesn't really flow unless you go to really fine grades, it doesn't flow bad. So you have your motor speed, and it's fine. If you increase the speed though, you see how you already have some weight variation, and you see how the motor speed has to keep up increasing to keep on the same flow. So it is actually struggling to the point in which here the mass flow, it is going down and down, and then it collapses and it doesn't flow anymore. That is MCC. And let's say we don't use SMCC or EasyTab, or we keep them separate, and you want to, of course, also put the CSD into the system, and what we see is this. That is a mess. I hope that you can see the image from, it's maybe, depending on the beamer, it's not clear at all. You can see that it's supposed to go out of here and into the pod, but you see how it's going everywhere, because it is a very, very fine material that is highly electrostatic. So just the moment you put it, you open the bag or you try to feed it, it flows, and immediately sticks to every surface that it can. And of course, everything is metallic, so it just loves sticking to everything. And you have it on the legs of the table, you have it on the pod, you have it on the... you cannot feed it. It's just straightforward impossible. And then the disintegrant in a similar way, you can to some extent also feed it, modified feeder or not, better in the modified feeder and macro feeder. This is not really relevant, but just to show you. Lubricant again is even finer, so even more difficult to make flow. Yeah, not so stable, but you can make it work. And this is Easy Tap. So on the other hand, of course, if you compare Easy Tap, it's a very, very well-flowing material. It goes really well at every speed. You create a flow of mass at the constant motor speed, and this, well, it's accurate feeding. Let's put it in a different way. Like, you can make it flow relatively well with the standard, already the standard large feeders, so you don't have to go into these specialized feeders. But if you do, you also see how it works very well in a granule feeder. The small note, what you see here is that I've been told that someone just forgot to put, like, it ran empty, so you have to put a bit more material, and that's why you see a jump, but in the end there's no difference. So the summary of this is that the feeding of EasyTab is much better than the individual components, and that is due to the good flow properties, and of course because of the morphology of the particles. And the conclusion is that the pure components are really difficult to feed. They're really difficult to feed compared to one. The electrostatic charging of MCC also is making some problems. CSD is, as we saw, absolutely impossible to feed, just like that. And then small feed rates of SSG and SSF, they cause challenges in feeding. So the thing is that if you want to do the same with the individual components, first of all, you need more feeders. You cannot feed it with just one hopper. So you have your line that is continuous, and then you have to put feeder number 1 for MCC, feeder number 2 for CSD, and CSD will not work, and then you have to take a step back and say, all right, so I need to co-process MCC with CSD, and then put it in one hopper, all right. But then I need your API, so another hopper. You need your super disintegrant, another hopper, and then you need your lubricant, another hopper. And they all need to work. But if you have EasyTab, you just solve all of that by just putting one hopper for the API, one hopper for your product, and then you run it. And you're minimizing the chances of something going wrong. Of course, if you have an absolute control about your process, you might solve all of those issues, but it's going to cost so much trouble. And now, mixing speed. All right, so you have it co-processed, right, but we have to mix it, and it's going to move through the line. And the question is this agglomerate, are they going to break? Are you going to just subdivide the particle into the individual components or something else? That is a question. Your typical 3 particle size descriptors, D10 or X10, X90 and X50, D10, D50, D90. This is the particle size, and these are different components. So what we did basically was take EasyTab and blend it, mix it, and move it around, and then put it in the laser diffraction and get a profile. And then we listed all of them, and we did a number of different things. This is Prosol Pure, so you see the gray one at the very left-hand side of it. And then you have Prosol Prosol 1 minute at 500 RPM, 1 minute at 1000 RPM, 1 minute 1450, and the same for 5 minutes, and the same for 20 minutes, bringing that to more of an extreme case. And what you see is that most of the time, and for most of the products, they all remain the same. So we said that it's really there is not effect on the mixing or the over-mixing of EasyTab when it comes to the particle size. So PSD is more or less similar for all samples, and the feed or mixing of it doesn't really have a significant effect on its PSD. And then the last step, and the last part of the presentation before the break is, all right, can we tablet it or not? Because of course the main goal is creating a tablet. If you cannot create a tablet, none of that matters, right? So we have 2 formulations, and of course the same. Formulation number 1, Prosolve API. Prosol number 2, 102 CSD, so MCC 102, your silica, your super disintegrant, your lubricant, your API. Same weight, same goal, with the small exception that CSD is straightforward, impossible to feed, as we saw. So we have to do a pre-blend. So there is already one more step here, so we need to take that into account. When you look at the calculated API concentration, so we're looking at the content uniformity more or less of the blend, fair enough, you don't see any big difference. So there is not really a big difference between EasyTab and the single components by the API. Give or take your rather similar standard deviation, looks good. But here we already start seeing something. When you tablet it at the same target speed, at the same feeding speed, you see differences in filling depth. So basically when you tablet, and most of you already are familiar with that, but you aim at the weight. So you want to do, let's say, 400 milligram tablets, that is your goal, right? So you have a blend and you trust that everything will flow into the die and you will be able to tablet. What happens if you don't get to the tablet weight that you want within a specific filling depth, that you increase it because you tend to think, oh, right, so we need to fit more powder in. So we already see how the first indicator of the flow is the filling depth. With EasyTab, you don't really need to go to 6.01, but you can keep here. So it flows better, and that's kind of like the first indicator we see. So also, of course, not only on flow, but on density. And when we look at the tablet characteristics, so we press those, and we see what the average looks like is that the average is, after even accounting for the standard deviation, it is higher. So the same compaction force, we get harder tablets with EasyTab rather than with the single components. And also, to some extent, the tablet weight is a bit more on point than it is with the single components, and that is because of the flow and also because of the density. So for single components, again, just to let you think of it, you need to do the pre-blend still with the MCC and CSD. The content uniformity, we also show here how the content uniformity is better for EasyTab plus API than for the single components. And I am convinced, because of everything that we've seen and explained before, if you make this process even longer, if you keep on running the system for longer, the differences here will be even bigger. So the content uniformities indicate a very good distribution of the API into the tablets when working with the EasyTab plus the API. The conclusion for today and for this presentation is that EasyTab, we believe, is the way of running a continuous processes because of the simplification that it brings. It really makes no sense to step into a continuous manufacturing process using your good old excipients. You need something else. The pure components are going to be challenging to feed. You're going to face a number of issues. CSD, it is straightforward, unsuitable for continuous manufacturing because of how poorly it can be fed. The mixing with high shear forces has no effect on the PSD, so that is not an issue. It flows better than just the blend of the individual components, and the content uniformity and the crossing strength are at least comparable, if not better, than talking about the pure components. And of course, the pre-blend needed of MCC and CSD for the physical mixture. And that was it. Thanks for your attention. If you have any question right now or during the break, you're free to ask away. Obrigado.
Perguntas? Alguém tem alguma pergunta? Bom, se ninguém tem pergunta agora, a gente tem um coffee break lá fora. A gente só vai fazer um coffee break agora mais curto, um pouco, porque a gente está tentando agora recuperar o tempo aí do atraso no início. Então a gente vai fazer uma pausa agora. Banheiros, para quem não sabe, não chegou e não viu, aonde estava o coffee break aí do lado direito, o banheiro masculino e o feminino do lado esquerdo. E a gente faz uma pausa de uns 10 minutinhos e retorna aqui. Tudo bem? Obrigado. Pessoal, a gente vai fazer uma modificação na agenda agora, por conta do atraso do início, né, que a gente teve que atrasar um pouco para dar tempo das pessoas chegarem, por conta do problema aqui na entrada da universidade. Então, a gente vai fazer algumas modificações, porque tem pontos da agenda que não dá para mexer, por exemplo, o almoço nosso, né? Então, o Guilherme vai apresentar agora o estearil fumarato de sódio, o PRUV nosso. Aí depois a gente vai começar a se encaminhar já para o almoço. Aí como vai funcionar? O restaurante ele fica próximo, mas a gente vai junto de ônibus. Então vai ter um ônibus aqui na frente esperando a gente. A gente vai embarcar no ônibus, vai até o restaurante, que é um trajeto super curto de ônibus. E lá a gente vai almoçar. Não sei se vocês conhecem, é o restaurante Sueden, ele fica na próxima faculdade de Economia e Administração. E o nosso almoço vai, sei lá, tem uma área reservada para a gente lá no restaurante, a gente vai ter esse almoço lá. Depois a gente retorna e dá continuidade com a agenda normal. Mas, antes do almoço, antes da gente embarcar no ônibus, eu queria pedir um favor para vocês. A gente gostaria de fazer uma foto, todo mundo junto, e a única oportunidade, ou a melhor oportunidade que a gente vai ter, vai ser antes de embarcar no ônibus para o almoço. Então, tem uma rampa aqui atrás, aqui saindo à esquerda. Se a gente pudesse posicionar todo mundo ali na rampa, é rapidinho, tirar uma foto todo mundo juntos, todo mundo que participou hoje. Vai ser muito legal para a gente registrar aqui nos nossos arquivos, né? Então é isso, gente. A partir das 12 horas. A partir das 12, isso. Então é daqui a pouco já, né? Então tem uma apresentação e depois a gente já vai. Obrigado.
Good. Questions?
Guilherme, eu queria perguntar um pouco sobre o ProSol Visitab. Nos exemplos que foram dados na apresentação, a gente falava de apenas um ativo para o medicamento. A minha pergunta é se você tem uma associação de ativos, mais de um API, como seria o comportamento, se existem estudos nesse sentido, ou até mesmo polivitamínicos, produtos com uma quantidade maior de ativos.
Yeah.
Você entendeu?
Yeah, I got it. I'm going to answer in English because I do not really trust my Portuguese. But thanks. It's a good question. We always position EasyTab as a ready-to-go product for multivitaminics and for other products. Whether we can achieve the same with multiple APIs is not something we've investigated right now, but what I would propose is to do that in different blending steps and then mix everything together. So it might be that you need an extra step, API 1, EasyTab, API 2, another EasyTab altogether. How does this translate to a continuous manufacturing line? It's a good question. I really don't know, but I'm sure that someone is thinking about it. I would say if you have the same particle size of both APIs, then it should not be a problem to do the same interactive blend. If you have a really challenging formulation with different APIs with different properties, then it's a matter of looking forward. But the thing is that you're going to need a different hopper for every API, so that is nothing that you're going to be changing with EasyTab, right? So you're going to keep your one hopper for EasyTab, and you're going to have to put different hoppers for the different APIs. So you probably have to do more in your hopper design than you will have to do in your excipient design. But again, it's a good question. I have no idea how that would translate in continuous manufacturing. In traditional blending, so if we look at the batch manufacturing, so it will be you fraction, you blend, you mix, you move on. Good. Any other questions about the rest of the things before we move on? Nope. All right. Good, we have one more presentation before we go have lunch, and that is Proof, which is our top-of-the-line lubricant. And the first thing that, of course, we have to explain, or maybe not, but I'm going to mention that regardless, is why do we need a lubricant in the first place? A lubricant is used in a formulation to keep it from sticking to the punches and to the surfaces and to the machine. It's important to explain that a lubricant is not a glidant, but has some glidant effect. That means when you have problem in your flow, lubricant can increase the flow, but it's not the main goal of a lubricant, because you might see it in the slides. Some people is using that in that way. Some people over lubricate or over blend it for that reason, but it's for now out of the question. So traditionally you use different lubricants. I'm going to explain some of them. Let's say magnesium stearate is so far maybe not the golden standard, so maybe not the best, but definitely the most widely used lubricant. And you typically want to mix it at the very end of your formulation. So when you have your blend done, you put lubricant outside of the formulation, if this makes some sense. So what you want to do is you want to mix it with lubricant, but not too much, and right at the end, so that you will prevent the sticking, but also not that much so that it will go within your formulation. It will have some interaction between how your interactive blending is happening, and you're going to have tableting properties lost. So tableting, the compactability of the blend will go down. You're going to have problems with your API segregation. You're going to have eventually problems in your dissolution profile because of the hydrophilic nature of the lubricants. So it is typically a overlooked. So the complexity of the lubrication is overlooked, and is something that we need in most of the formulations. So Proof is sodium stearyl fumarate, is our top-of-the-line lubricant, and is what we think also makes a lot of sense for a lot of formulations and solves a lot of challenges. And I'm going to explain a bit on how does it do what it does and why is it so important. But again, first, the purpose of lubrication, as I explained, is to get the blend, to avoid the blend from sticking to both, basically to every surface that is exerting some pressure on the blend, that being the top punch, bottom punch, and also the size of the die. So you want to reduce that friction, and by reducing that friction, you're gonna A, keep your tooling in place, so you're gonna have less tooling wear. B, you're gonna keep your content uniformity in your tablet size and shape and shine in a better way, and you're gonna avoid some of the problems. Anti-adherence, so of course it's not only the friction between the walls and the blend, but also how much is going to stick to the punches. So of course, if you want to make the experiment, just take a sugar, or you can take lactose, for example, and you run it in your press, and you run it for a long time. You run it at high pressure, and you don't put any lubricant at all. You're going to see how the tablets are going to look less and less shiny, and then at some point it's going to be sticking into the punches, and then at some point your tablets won't have the same shape and size that they used to. That's sticking typically. Good. And this is how a tablet will eventually look like. So you see that there is like a layer of powder that is missing because it's just stuck to the punches. Some APIs stick more than others. Not always the problem applies to every formulation, or not always in the same way or to the same degree. So, commonly used lubricants, what do we use for this? So we have a lot of traditional lubricants here, and we have some new ones. We have some hydrophobic lubricants, the very well-known magnesium stearate, among others, so some other stearates, so calcium stearate, stearic acid, hydrogenated oils. They are insoluble, and this is the amount that you need to put in. So of course you don't want to put a lot of it. Most of the times you don't need to. Sometimes you need to go up to 4%, which is a lot. And you want to blend it, again, in the end, really fast, and done with it. You have your hydrophilic lubricants, so FCF is the example here. And the reason why we say it's partially soluble is because, well, you're going to see in the formula later, it has some some soluble region and some region that is not soluble. This has an influence, of course, in the dissolution time. We're going to show that later. So it's a big advantage that is partially soluble instead of fully insoluble. And you have inorganic materials, so your fumed silica, which is most of the time a glidant, but also can work as a anti-adherent and talc, which is also rather old and not so good as magnesium stearate, not so good as SSF either. So this is SSF. This is how it looks like under the microscope. It is highly efficient. It is less hydrophobic than magnesium stearate, so it will be more soluble, so it will hinder your formulations less when it comes to dissolution times. It has a very well-defined particle shape and size and a specific surface area. It has a high melting point, which is very important because you can work at higher temperatures. It has a neutral taste. For some people, maybe not relevant. For some of the formulations that are a bit more sensitive to the organoleptic properties, yes. This is how the molecule looks like. So basically, you have your hydrophilic structure here that is highly polar, and then you're going to have that part, more likely to go into water, and then you have your 17 or 18 carbon chain that is highly lipophilic, your regular oil chain that is, of course, not soluble. It's highly pure and has a really, really high batch-to-batch consistency. So, what are the problems with using lubricants? There is a number of things that have to do with the process. There is a number of things that have to do with which APIs are you tableting. And of course, there is a lot of incompatibilities. So magnesium stearate has some problems with some APIs. There are things that you cannot tablet with magnesium stearate because they are incompatible. That means that you need to look for some of the solutions. Proof could be one of them instead of mag stearate. The concentration is, of course, a problem with some of them. As we saw, you have to go all the way up to 4%, which is a lot. And some might work already at 0.25. So the more weight that you put in a formulation in a blend of these, the less space you have for your API, your binder, or whatever it is that you need to put in. And remember, we do not want to, excipients is something that you traditionally want to put not a lot of. We need them. We cannot avoid them, but then we need to select which one we want to put in and which amount. So it's important to be able to minimize what we can. And of course, by doing that, you can also reduce your tablet weight and eventually your tablet size. That's another advantage, as it is with SMCC, for example, coming back to the question. You can do a lot of over-lubrication and over-mixing. We explained that before, remember, when we saw all of how the tablet hardness dramatically drops when you overblend. So when you overblend your lubricant, if you put a lot of it, it will go in between granules. The granules will not stick to one another, and then your compactability is going to just drop. Because they are not so soluble, they are going to get in the way. So when you try to dissolve your API in water, if you put too much lubricant, you're going to see that eventually. The stability is going to also be compromised by this, by two reasons: because you're putting a number of ions in it, and because you have some fats that will become rancid, of course, with time because of the reaction with oxygen or not. And then there's a number of marketing aspects: the taste, the appearance of the tablets, that you might have a problem with some of these lubricants. Particularly with magnesium stearate, and we're taking this as an example because it is the most used lubricant, and basically it has a number of problems that we're solving with proof, and that's why we present it. It is very hydrophobic, and this is also one reason why it works very well, but it hinders the disintegration time. So if you have something that has to be an instant release tablet and you're working with magnesium stearate, you're already putting a stone before your feet, and it's not going to work. It is very sensitive towards mixing. The tablet hardness drops very fast when you overdo it. It has a film formation in the effervescent tablet because of the high hydrophobicity. So if you want a formulation that has to interact with water, it's gonna be a problem. It has a lot of incompatibilities sort of with APIs. So it's a whole list of APIs that you just cannot or should not formulate with that because they're going to have an effect on the stability. It has a metallic taste. Again, might or might not be relevant for your formulation, and a lot of Nutra formulations will be a problem. or could be a problem. And it has typically more of a batch-to-batch variation. Of course, this depends on your provider and who is manufacturing that, but it is so. It's not a process that we have as controlled as we have SSF in the production. Proof is less hydrophobic, so it has a shorter disintegration and shorter dissolution time. It is particularly nice for effervescent tablets, so if you're formulated with that, give it a go. It has a better taste, or at least it doesn't really have this unpleasant metallic taste. It is less mixing sensitive, as good as no mixing sensitivity. There is some sensitivity, but nothing like magnesium stearate. Because of the way it is produced, it is very consistent in batch to batch, and it is robust and chemically stable. So you are avoiding a lot of those API incompatibilities. So if you can reformulate something with SSF instead of max stearate. Good, but then why is the question. It has to do with the shape it has, and it has to do with how the particles interact with the bigger particles in the blend and how it sort of coats this particle. And this is an example on the left-hand side. This is how it looks like with magnesium stearate. What you see here in the gray is the powder mix. Imagine just one single particle of it. So that is your, I don't know, your chunk of granulate. And then you put your mag stearate outside. Mag stearate is typically really fine. You do it, you blend it, and then it forms a film. It sticks to the surface of the particle, and it makes a continuous film, which is something we really don't want, and I'll explain why. Proof, however, is because of the shape it has. It's like a bit of a flake that will stick to the particle, but not make a continuous film. And you have these gaps. So you have a lubrication that is good enough not to create any sticking and not to create the high ejection forces, but at the same time, it really allows a bit of room for, a breathing room for not having this continuous line, interactions with water and so on. So you don't want this continuous film. And the reasons are, like, the dosage might be too high, so maybe if you overdo it, of course, you're gonna completely coat your particles. If it's completely hydrophobic, then it's going to stick and the water won't go in because you're just creating a film that is going to protect the granule to go into water. Could be because that you mixed too long, or maybe you did not mix too long, but your process is taking time. And as I explained before, your sample has to go through the hopper, and it's going to vibrate, and it's going to go into the continuous or the non-continuous tableting process. It's going to keep on vibrating, keep on mixing. So effectively, your mixing time will be too long, and maybe your temperature will be too high, and if your temperature is too high, it will melt in a way that it was going to make this, but you really don't have that with proof because the melting point is over 200 degrees, so it's really stable. So we see, once again, an example on the blending. So on red, you see Vivapur 102 with magnesium stearate. What we did here was blending for quite some time, and then we were testing the crossing strength on the tablets that we collected at given time points. And you see how the longer you blend, the lower the tableting strength is. So you're like losing 60% of your crossing strength over time when you overdo it. And you see how much this effect is hindered with proof. So you really are not dropping that much. It is insensitive to mixing time. What we say is insensitive because we're looking here at 1 hour, which is nothing that no one would ever do in a mixing process. But if you look between 10 and 20, or maybe between 0 and 10, here you already see some differences. And those differences, they're going to keep over time. So, the temperature too high. So this is a melting point of a different number of lubricants, and depending on what you use, you're going to have one or other melting time. Proof is all the way up here, which means that it's really unlikely that you will ever reach to 220. So if you don't reach there, you're going to avoid this melting that will eventually cover all of your granules by creating this continuous film that you want to avoid. But if you work with something like magnesium stearate, maybe you don't need to go all the way up here, but you're going to see it. And if you go down hydrogenated vegetable oil, some other alcohols, some other stearic acids, the temperature that you know, around or between 50 and 60, you already see some melting effect, and this is gonna translate to this continuous film that we're trying to avoid now. So we wrote a case study, which is part of a PhD of Ines Anioki in 2014, which is the suitability of proof for the direct compaction of sorbitol, which is in hydroalcohol, and then we do it with MCC. So we put 75% of sorbitol, 23% of MCC, and 2% lubricant, which is quite on the high side, either proof or max steroid. We're going to tablet it with flat face punches. It's also an extreme. Typically, you have convex punches in the industry. A flat face sponge, because of the structure it has, it will favor sticking to some extent, and you want to avoid it. And the tablet weight target was 300 milligram. And we checked on the hardness, and we checked on the compaction forces of the tablets that were made with proof or with magnesium stearate at 2 or 4%. And we see that the two bottom lines are magnesium stearate. Of course, the higher amount you put of magnesium stearate, the lower the hardness of the tablet is. But even at the same really, really high example of how much we can put, because we should never reach a 4% in a formulation, even at that extent, proof overperforms magnesium stearate. So we claim that is a higher tablet hardness achieved with proof when we compare it with magnesium stearate. And then we see the same in the disintegration time. So if you have a disintegration time plotted for magnesium stearate, it is between 200 and 300 seconds. If you do the same with proof, regardless, or pretty much regardless of how much you put, 2 or 4%, you keep it under 200. So you have a difference of roughly 100 seconds, so almost a minute and a half or almost 2 minutes at every compaction force. So if you're looking to work with something that is poorly soluble, for example, and you really need to increase that, you don't want to work with magnesium stearate. You want to work with something that is more soluble. You want to work with a lubricant that is not gonna pose any more difficulty that you already have by working with a lipid soluble API. This is the influence of the concentration. So even at a rather low concentration, you can get the tablet done. And this is also the disintegration time plot. So you have the total lubricant concentration, what we work with proof, and the tensile strength of the tablet. And you see how, regardless of 0.5 or 2%, the disintegration time stays the same. The tablet tensile strength more or less stays the same. This being proof, and this is magnesium stearate. And you see how the higher you go in the concentration, magnesium stearate just drops. We have the influence of different lubricants on this solution, and we compare 4. FCF, so proof, magnesium stearate, stearic acid, and sodium stearate. And we do that with paracetamol. So this is your compaction force, and this is your tablet hardness. This is a compactability curve again. We see how much better actually stearic acid is, to the point that the tablet hardness is really high, but this will come at the price. We'll see that later. Proof is still better than sodium stearate, and this is still better than magnesium stearate by quite a long shot. This is the lubricant effect on the ejection force. Stearic acid working very well, and the rest are relatively, to be compared. This is the lubricant effect on tablet disintegration, and this is the compaction force. So magnesium stearate is all the way up here. So when you really do this experiment, you see how the disintegration time is maybe, and compared to the rest, not acceptable anymore with magnesium stearate, and proof still overperforms in the line with the other two. Good. And this is where we see really the difference. So from minute 0 to minute 20, this is your typical dissolution graph, you see how proof formulations, the blue line, quickly goes all the way up, and in 10 minutes, 20 minutes already outperforms the rest. So it's really the fastest way of achieving a dissolution when it comes to lubricant choice. There is an influence in the particle size, and this also relates to the way we build this film or not in the granules. So we took 3 examples here, micronized, so really, really fine, in blue, regular, and in green, and very coarse in red. And the amount or the size of the layer depends on the size of the particular lubricant. So of course, if you micronize it and you blend, you're gonna create a different thickness because it's gonna land on top of a particle that is already sitting on top of the granule. So you're gonna make a bigger one. And this will have an effect on the tablet cross itself, on the disintegration time, and also on the ejection force. We have 3 different grades of particle size of proof. We have regular proof in green, we have coarse grade in red, so a coarser proof, and also we have a micronized. And we see there is a small increase in tensile strength when we look at the coarse grade, but it's really not that much compared to our regular proof, and definitely, well, a bit bigger, but also in line with the micronized. And what this shows is that regardless of the particle size that we use, the tensile strength is still the same. Of course, it's going to be a problem with using micronized FCF because of dosing, mixing, and different things. It's a new world of problems. It's a different dimension. But regardless of the size, it lubricates very well. Here is where we see the problem. And of course, if you work with micronized SSF, what you do is you build layer on top of layer on top of layer, and that's going to hamper the disintegration time. So you want to work with something that is either normal grade or coarse grade, so that you're going to have the lubricant effect, but you're not going to overdo it in a way that is going to create this layer that will make more difficult for your tablets to disintegrate. So that is a key point here. We're not offering this grade for obvious reasons. And this is how it looks in the ejection force. So of course you want to have lower ejection forces. The smaller it is the particle size, the better the ejection force will be from 10 kilonewton onwards, but also you don't really see much of a difference here. So this is more than acceptable for normal proof, and maybe you need coarse grade, but it's sometimes not needed. But when you keep that picture in mind, micronized is not really an option anymore. So as a summary and as a takeaway point for you today before we go to have lunch, why and when should you consider proof instead of magnesium stearate or talc or whatever it is that you're using for lubricant? If you have problems with your tablet hardness, so if your tablets are suffering with time typically, if you have a big batch-to-batch variability that you cannot really explain by anything you're doing on any other excipient you're buying, might be the lubricant. Don't oversee that. If you want to scale up, but you're really scared that you're going to mess up with the lubricant step, which happens because it is not the same working in a smaller or in a bigger equipment. And it's not the same the moment you change the blender, the moment you change your tableting equipment, the hopper, everything changes, and you cannot use one for all with magnesium stearate, but you can do it with proof, because we've proven that is bulletproof in this sense. So there is less likelihood of overmixing, and you're going to have blending times in production, so you're going to let them sit and restart, and you can do different things. You don't have to blend right away, and you don't have to do it in the same way that you do with magnesium stearate. You're going to gain some flexibility. You might blend for longer or let sitting and then blend with proof. If, of course, you have an incompatibility in magnesium stearate and you cannot include it in your formulation, think of proof first. And again, there is a list, and if you're working with APIs that are magnesium stearate incompatible, then you're gonna know straight away. If you want to reduce your fill formation in effervescent tablets, if you're working with effervescent tablets or with poorly soluble APIs, if you need to avoid every small hurdle that will hamper the dissolution of your API, think of proof. And of course, if you need, as I say, a fast dissolution, if you need a really fast release acting and you want to minimize all sorts of problems, also forget about magnesium stearate and go for proof. That was it for this morning. I have one more presentation that will come after coding at the very end of the day. I'm really, really looking forward because it's our launch for this year, and it's a product we are particularly in love with at JRS. I'm going to talk a bit more about it later after the coding session and after lunch. Thank you very much. If you have any question, I'm fully available right now or later. If you want to ask also in Portuguese, I might be able to understand, but I'm not completely sure. Yeah, thanks. Any question? No? Good. If you have one at any point, just I'm really approachable, so just like say hi and that's it. Thanks.
Obrigado. Em comprimidos mastigáveis, o PRUV ele não vai evidenciar o sabor como do estearato de magnésio na formulação?
I'm going to review the question because I'm not absolutely sure I understood everything. In chewables, right, is the question?
Yes.
If it's an option or if it's... so I think it's a very good fit.
Eu queria saber se o PRUV, nas formulações para comprimidos mastigáveis, ele não vai apresentar sabor desagradável como o estearato de magnésio.
No. I cannot really tell you what is the exact flavor profile of proof, but it's avoiding the metal tasting of, so it's more neutral taste than magnesium stearate as well. And it's also a perfect example, and thanks for bringing the question up, because it is, if you want a really fast release of your API, or you want to mix it with the saliva, as you don't want anything very fatty. So it's a perfect application for proof. Also, in the case of ODTs, you typically want a really, really fast release of the dose in your mouth. So for ODTs and for chewables, is a very good product. Yeah, but again, the taste profile thing, I can only tell you it's neutral taste. And it's much better than magnesium stearate, but I cannot really tell you how it tastes like because I haven't tried it myself. So. Thanks.
Mais alguma pergunta? Bom, se ninguém tem mais perguntas, eu vou pedir para vocês, para a gente tirar aquela foto que eu falei antes, ali na rampa, saindo aqui à esquerda, e de lá a gente já vai para o ônibus que vai levar a gente para o almoço.
About trends. And to bring your mind a little bit in the right position. So try to imagine that you are going now to an airplane. And this airplane takes you on a long flight, maybe to Europe. And you are starting to move in the airport, you are still on the ground, and then you are speeding up. You are increasing the height, you are increasing the speed. This is something like a picture for a trend. A trend starts slowly, and nobody knows exactly what is going on. And then you get more and more supporters for the trend, and then the trend is speeding up. And then there is a phase of stability. You are now, let's say, 10,000 meter height. The weather is nice. a lot of options. You can order something, you get something to drink, you have to make a choice, red wine, white wine, beer, whatever. So the trend is progressing, and you have a lot of options. We will come later on what can happen in this flight as well. But now we are flying on a stable flight in nice weather. So what is the trend? What is the trend in the pharmaceutical industry, especially regarding coating? This is not a trend. Oh, I have to go closer. So, first of all, trend number one, and this is not a trend we have since a year or 2 years or 3 years. This is a trend we already have since 20 years or even more. So less chemical, more natural. And when you look at coating polymers, I mention here 2 examples. Very chemical polymers, like polyvinyl alcohol, like acrylates. This was the past, and it's still, in present times, still existing and plays an important role. But now, natural source, but chemically modified. It's coming more into the business. One example is HPMC. It's a cellulose, natural product, but chemically modified. And this is something in the last 2-3 years. The industry is moving to real natural polymers, mainly driven by nutraceuticals, but pharmaceuticals are following. And one example are alginates. And we will see later on, one product from JRS is the VivaCoat Ocean Pure, which is basically just a natural polymer and a plasticizer, nothing else. By the way, when questions are coming up to your mind, you do not have to wait until it hurts. You can interrupt me anytime, and I'm happy to discuss this when it's popping up, not at the end. You may forget about it in between. Okay, colorants. You all know that in the past, a lot of aluminum lakes, synthetic colors were used. And then, let's say in the last 20 years, natural source but modified colorants became more important. And one example are iron oxides. So what do you think? Is iron oxide, it's a natural product or not? Just an opinion. Yes or no? Yes. What you are saying? Yes. Somebody else to have 3? I say no. But your answer, it's very typical, because a lot of people believe that you can find iron oxide by digging, a hole in the earth, and then something red and something yellow and black is popping up. Yeah, it's maybe true, but this is not used in the industry. What we use in the industry is chemical. It's chemical. We know it, but in this case, we are not important. Important is the patient or the consumer. And they believe it is natural. That's why for a lot of companies, iron oxides are still a natural source. So nothing wrong with it. But real natural are things, when you use coloring food, when you do extracts, for example, out of vegetables, sometimes flowers, this is something real natural. But there are disadvantages. And the disadvantage is the stability. So the industry is moving into that direction, but there are limitations. For example, stability of the color. and in some cases even price. You know, iron oxides are very cheap. And these colors could be very expensive. So plasticizer. When you remember a coating formulation, you have something like HPMC, and then you need, for the polymer, you need a plasticizer. The most common one is PEG, polyethylene glycol. Different ones, liquid ones, solid ones, 400, 4,000, 8,000, but it's pure chemical. It's chemical synthesis. So what we use now, especially for nutraceutical products, are medium-chain triglycerides. It's the same thing, natural source, a little bit modified. And now it moves to really natural product, to glycerin made out of plants. So you can see in different strains regarding the ingredients of the coating, it's all moves from chemical over semi-chemical, half natural to natural. This is a fundamental trend. Number 2. And this is something we will look in more detail. So when I say inert nanoparticles, no inert nanoparticles, then everybody, it's maybe thinking about titanium dioxide. And this is a topic for the next couple of minutes. But I want to make you aware of the fact a small nano-size particle, inert particle, is not just only titanium dioxide. It could be talc. It could be silicium dioxide. It could be iron oxide to a certain extent. So we should be aware that the discussion we have now about the bad impact of titanium dioxide is not about the chemistry. These particles do not react in the body at all. They get not metabolized. They get not diluted. They just harm the body by being physically present as a nanoparticle. And for this physical presence, doesn't matter if it's titanium dioxide or talc, for example. Just the size and the shape matters. You can follow what I'm saying, or it is too strange. Good. Thank you for that. So when we go back in history, over 50 years in coatings, titanium dioxide was used. Now in Europe, and you will see that a couple of slides later, there is a law in place for nutraceuticals and food. Titanium dioxide is banned since August this year. So even international brands, for example, like Centrum, they had to change their formulation. They cannot sell their multivitamin, multimineral tablets in Europe anymore by using titanium dioxide in the coating. Yeah, seems to be easy to change, but we will see at a later stage, it's not that easy. What we are talking now in the industry, and this is something like stand of the knowledge, to replace titanium dioxide by calcium carbonate or magnesium carbonate. It works to a certain extent. You can use it, but the titanium dioxide is in the formulation to create a high opacity. Opacity, I see this in the eyes, it is how effective you can cover something. It's the same like painting a wall. When you paint this brown wall with a white color, this white color is using titanium dioxide. Or when you have a good color and you paint it once, the wall is white. When you replace the titanium dioxide by calcium carbonate or magnesium carbonate, you paint it once, and the color of the wall is still brownish. and you paint it twice, and it's maybe still a little bit brownish or yellow. So you have to put it 3 times on top to get it really white. That makes the difference. So these alternatives are theoretical alternatives, but you cannot expect the same performance. This is the point. And now, and this is something we will talk in more detail, naturally occurring organic compounds are used to increase the opacity. For example, modified starch or sugars. Trend number 3. And now it gets a little bit, let's say, challenging and revolutionary. This is maybe something you never discussed before. And it's one of my favorite topics, to be honest. Separate functionality from coloration. So that is basically meaning when you have a functional coat, could be enteric, could be moisture protection, could be taste masking, could be odor masking, take the pigments out. And when you need a color, realize the color via a top coat. And this is something like a fundamental change in thinking, and there are 2 reasons. We are doing this even before the titanium dioxide ban in the European Union. Because in the last 10 years, we faced a lot of limitations regarding regulation of colors by the European Union. Some aluminum lakes were banned, other ones were just allowed to a maximum amount. And imagine you have an enteric coat. This enteric coat is red. And you use an aluminum lake in this enteric coat. And now this lake is banned by the regulatory body. You have to start from scratch. This is not just that you change the color, you change a functional coat. And you have to show that your API has the same bioavailability. This is a lot of work, and this is a fortune of money. When you separate the functionality, your enteric is untouched. You just change the color, and you may just do 3-6 months regular stability and fine, and nobody will take care. So this is the fundamental thing. And now with the titanium dioxide, it's getting even worse. Because titanium dioxide is included in all coating formulations except clears. So not only the white. Some people think, oh, I have a blue coating, there's no titanium dioxide. No. In this coating formulation, it's maybe 27% titanium dioxide and 3% blue. And in the yellow, it's the same. So all not clear formulations containing titanium dioxide. We should be aware of this. And now, all the people, they are full of fear that maybe even in the pharmaceutical industry, they have to replace titanium dioxide in the formulation, and when they have an enteric coat, they get really nervous, for good reason. So this is just to give you an idea. This is a basic coating formulation. It doesn't matter who is the manufacturer. So could be, I don't know what, could be JRS, could be Colorcon, could be Ashland, doesn't matter. There's the same principle. Half of the formulation is a polymer, which could be the HPMC, could be the PVA, and 1/3 are the pigments. So titanium dioxide, iron oxides, aluminum lakes. 1/3 you have to replace. This is a lot. This is a lot. And then you have plasticizer, 10% of the polymer, and detachifier, which is mostly talc. Another, problem ingredient. So I'm struggle here with that. So final trend. I said that in some cases, the nutraceutical industry is going, let's say, ahead, and pharma is following. Give you one example from an ingredient like HPMC. You may know that we have in Europe since, I don't know, 15 years, the rule that when you use genetically modified organisms to produce some ingredients, you have to show it on the packaging. So it's not forbidden, but you have to show it. In practice, not for pharma, but for Nutra. In practice, it means when this is showing up on the packaging, 99 from 100 potential customers will not touch. So that it's no way. And this is only for Nutra. But when you are selling HPMC to a pharmaceutical company in Europe, they are asking for GMO-free. Even if there's no rule, there's not a must. It's just the expectation level and to be on the safe side. And that makes, by the way, the difference between manufacturers of HPMC in Europe, US, Japan, Korea, to China. So outside China, they use wood. In China, they use soybean colors, soybean raw material. End of the first part. Any questions? Questions? You do it? Okay. I'm struggling with this here, so maybe we change to the other one. Viva Code Free is the next one. So back now to the model of the flight. You know, we already started. We are flying now. Everything is stable. And you get now the information from the captain, fasten seatbelt. So normally when you see that or the design is popping up, something is going wrong. Maybe the captain expects some thunderstorm or whatever. And the interesting thing is, you do not want to have the thunderstorm. I do not want to have the thunderstorm. Even the captain of the plane doesn't want to have the thunderstorm, but it is there. And this is the ban of titanium dioxide now in Europe. This is something like a thunderstorm. And what it's doing with the industry is like when you touch the thunderstorm in the plane, boom, 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 boom. So they all totally nervous. And the nutraceutical industry already switched. But pharma, they received, you know, the sign fasten seatbelts, 2 years' time. And then the thunderstorm comes for your industry. So they take it very serious. They're asking now for samples from all these suppliers and putting all this on stability and look what's going on. And we are running around, you know, doing presentations here and there and asking questions, supply new samples. This is the situation in Europe. And this is the situation even in the US. Because big pharmaceutical companies, first of all, they expect that the ban of titanium dioxide will come in 2 years' time for pharma as well. Even if it's not Europe or only Europe, this has an impact on the rest of the world. A lot of companies will supply or want to supply their products globally. And remember the picture I mentioned, this is not GMO-free. And when you have to put a sign on your packaging, this contains titanium dioxide, you know, it's still in the shelf, nobody will touch it. And for the generic industry, for example, products like ibuprofen, metformin, mass products, when one big player in the game will switch the product to titanium dioxide free, even if there is not a regular need, this will give an advantage, and then the others will follow. So this is something like, it's unstoppable. Nobody can row the boat back at this stage. So what is JRS doing in this case? Maximum opacity without titanium dioxide. And we are talking now about our solution. It's called VivaCode Free, because the VivaCode Free, it's not containing titanium dioxide, and it's not containing talc. Remember, at the moment, no need to ban talc. Not in the European Union, not in the US. But the story about nanoparticles, you know, we are in the middle of that, not at the end. So that's why we try to do it without talc. The other good thing, this VivaCode Free formulation you can get in any color you like. So that means we do the color match. You choose the color, and we prepare the coating according to your wish, or based on the Pantone number you are supplying. Maybe for your memory, or for those of you they are interested why we started the whole discussion about titanium dioxide. It comes from the food industry, and especially cheese. You know, in France, they put titanium dioxide into cheese. To do what? Anybody idea? To do what with the cheese? Say it again? Yeah, to make it white. To make the cheese white. The consumer wants to have, let's say, mozzarella should be, you know, white. The whiter the mozzarella, the better the mozzarella. And to do it just with the milk, it's not enough. They added titanium dioxide. It's not, I'm not joking, it's really the case. The same thing with orange juice. You know, oranges are relatively expensive compared to water. And when you not using a lot of oranges, then the orange juice is not getting turbid. It's getting transparent. And customers, you know, they look at the orange juice and say, oh my God, that could not be a good orange juice. You know, it looks like a lemonade. Make it turbid, put in some titanium dioxide, and then you have a proper orange juice. This was the starting point 3-4 years ago in France. Just for you to get a little bit of understanding of the background. Maybe there's a good reason that people are not putting titanium dioxide in cheese and orange juice. I believe so. The bureaucratic people in the European Union, they cannot, you know, differentiate between kg of titanium dioxide in orange juice and milligram or even nanogram in a tablet. For them, it's too difficult. That's why they implemented the ban for all of us. Okay. The scientific background, I mentioned a little bit about this, is a physical impact. And the explanation is something like that you absorb in the gut these inert particles, and that they stay there and harm the human body. There are different views. When you go to the literature, you find now even good resources telling you that it's harmless. But at the end, it doesn't matter. It's once in a world, and nobody nobody investing a lot of money, especially not the titanium dioxide industry, to show that it's harmless. So we have to say goodbye to that. So as I said, August 2022 is the ban. And the warning sign for the pharmaceutical industry is something like 2 years' time to do investigations and to do stability. So when you do, all of you are close to a coating process. They know that it's so important that you have a smooth process, that you can apply relatively high solid content, that you want to achieve a smooth coating surface. The coating should show high adhesion to the tablet. These are fundamental things. And our VivaCode Free, we developed in, let's say, with such a goal that you can use it in the same easy way as a regular HPMC-based coating or as a regular PVA-based coating. Nothing special. No special preparation, no heating, additional stirring, sieving, all this, not. So when you are using now from us or from our competitors a ready-to-use coating system, you can use our VivaCode Free in the same way. Weight gain. When you ask now some of our competitors to get some samples, titanium dioxide-free coating, they will send you something, and they maybe give a recommendation that you have to apply 7–8% weight gain. Weight gain tells you something is the thickness of the coating on the tablet. We believe 5% weight gain from a practical standpoint, it's enough. More is causing problems, is creating, let's say, roughness, is creating brittleness of the coating, and makes the whole process extremely long and expensive. So that's why when you have to apply 7–8% weight gain, from my point of view, this is not a solution. In case of the VivaCode Free, 4%, it's enough. So what you can see here, we used black tablet cores. Worst case scenario. Most of the pharmaceutical products are not black, thanks God for that. In nutraceutical products, sometimes they are very close to black. So for that reason, you have to cover it. So we choose this black core, and we applied an HPMC-based coating, 3%, 5% weight gain, and we did the same with our VivaCode Free. And you can see here, it's depending a little bit on the quality of the beamer. You can see here, with 3%, it's still a little bit dark, but with 5%, you achieve the same opacity as with titanium dioxide. And this is something extraordinary. And that leads me to something I would like to ask you. When you really start to develop titanium dioxide-free coatings, make your own opinion. You know, they are nice people, like me, like Rudy, telling you nice stories. This is fantastic. Some of them it's true. But make your own opinion. Ask for samples, apply this on your tablet, and then make your choice. The only thing I would like to ask you is keep us in the loop. When you do the testing, we have no fear regarding the competition. When you do the testing with all you can get, but make sure that you get the VivaCode Free from JIS as well. And then you make your opinion. So we are really, let's say, convinced about the result. So what about colors? What we did here is a very, very simple thing. This is all titanium dioxide free. 5% weight gain with the VivaCode Free. And we did a mixed batch. This batch was half white tablet cores and half black tablet course. So we applied the same coating. And this is the result. And I can even show you if you want. Maybe you can, this pass around. Maybe both, yeah. So you can play with it, you can break it apart or whatever, you can take it home. So it is a solution working for white coatings and working for colored coatings in the same way. Process parameters. We tried to develop a coating which is in line with an HPMC-based coating you regularly use. You can see here, weight gain 70%, tablet bed temperature between 36 and 40 degrees, nothing exotic. Something regular you are familiar with. And you know, for R&D people, this is not the problem. They can adjust everything. The problem is the production. And the production, you know, they do not want to change their thinking, their handling, their way of doing. So that's why we try to keep in the same parameters. And the weight gain up from 3 to 5%, but 4% it's seldom needed. So with 5% you cover a black tablet. For your tablets, probably 3% or even less is enough. But this is something you can easily find out by yourself. Viva Code Free. Thank you. Should I go on for the break or? Yeah. Okay. So there's still some attention, I hope, from your side, or you need a break, or another not more than 15 minutes with me, and then a break. So the molecular structure and the quantitative composition, yeah. You know, there's a very easy way to get to this. So you ask Valdomero or some of our Brazilian colleagues to get a sample. You test the sample, and when you are convinced by the sample, you sign a CDA with us. Yeah, especially university, you know, this is always so. No, we do not make a secret out of that. And when you want to sell a product in pharma, of course, you have to share the quantitative composition. Otherwise, no chance. Yeah, but we are not, you know, I'm not flying around the planet and tell everybody, look, this is the composition of our Viva Code Free. This is the best in the market. And then everybody from, I don't know, Kenya up to Greenland is starting to copy it. Yeah, especially, you mentioned it, yeah, especially China or even India. Yeah. So we said, to give an honest answer, for the pharmaceutical industry, because there is no need, there is no commercial big sales so far, because why should somebody buy this? So they test samples, and some of the big ones, they ordered 25 kg, 50 kg for a production trial.
At least say if it's similar or something or completely different from this one. This is one of the best. This is a Japanese, you know, substance that I use in my lab.
Yeah. So this is no. 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 This is not PVA based. This is something I can tell you. And another thing, when you are insisting, you know, and I want to make you a little bit happy that you get a good answer. So the fundamental polymer is HPMC, but it's not alone. And I can also tell you it is not working with PVA. And it's not working in the same way with methacrylates. There are solutions, we have solutions even for PVA, even for methacrylates, but not with the same opacity. The question is, do you want to paint the wall once or 3 times? So when you want to paint 3 times, you know, when you're highly motivated and you enjoy the fun of painting, then you get a nice solution even for PVA based. If not, I would recommend VivaCoat Free and you paint once and enjoy. So this is, and we really investigated the last 3 years quite a lot. And that's why we recommend, this is one of the reasons we recommend to split coloration or pigmentation, I have to say pigmentation from functionality. So what do you think is the function of a titanium dioxide or talc or, I don't know, iron oxide in an acrylate coating or in a PVA-based coating? There's no function. No, the contrary. The functionality is less the higher the pigment load, because all the pigments are sitting in the functional film and disturbing the business. So when you pigment your enteric coating, you have to apply more weight gain to get enteric performance. So even if you do what we recommend, let's say a two-step coating, maybe the total amount, it's still less. This is a thing a lot of people have not in mind. When you just use the functional polymer and do not disturb the functional polymer by pigmentation, it is much more effective. So we will talk about VivaCoat Protect, which we supply in white, and now titanium dioxide free in clear version. And when you want to have a certain color, you can add VivaCoat Free on top, or you can add on top what you want. And all of our coatings, when we recommend functionality step 1, coloration step 2, are designed in such a way that you do not have to interrupt the coating process. Very important thing. So it's not that you apply PVA, take everything out, dry it, take everything out, cruise around the room, put it in again, and then add a color top coat. No. You can run the coating process. You have to be a bit carefully regarding the parameters, but we help you in this. You take out the tube of one vessel and move it to the other and let it run. So this is JRS solution. So high functional pharmaceutical coatings. So what are functional coatings? We mentioned this a couple of times already during my presentation. Remind me, enteric, moisture protection, taste masking, odor masking. This is what I'm talking about now. Not colored, not colored. So this is the whole line of our products. I do not want to go into detail and confuse you completely. This is our best HPMC-based coating, VivaCoat A. It's HPMC and polydextrose to increase adhesion and allow higher weight gain. This is our PVA-based system. This is I know that a lot of you are buying from our main competitor. Now they use the 2 version of that, and you hardly find a difference. By the way, you can get even PVA from us when you are interested. Produced in Japan. This is another thing I would recommend to you. When you try PVA and you get something from China, this is industrial material. So the only, let's say, producers of pharmaceutical grade of PVA are coming from Japan. They're all using this. Even our main competitors are doing this. Good, and we are talking about this range. Enteric, water protection, taste masking, UV protection. So let's go forward. This is a ready-to-use system. You use in the same way. You know, you stir, you create a vortex, and then you apply it. aqueous, 20% solids, tablet bed temperature, very similar. And here you need, of course, a higher weight gain because it's enteric. So I think there's no need in this room to tell you why you apply an enteric coating system, so we can skip this slide, I guess. The same as with this. So what we did, and this is probably more interesting, we did some case studies with two typical drugs. So one is diclofenac, the other one is aspirin. And when you compare now the release profile, and we always use the standard in the market. For enteric coating, there's one company, it's a German company as well. They are specialized in this since 100 years. So we choose this as the reference. And when you compare here competitor versus VivaCoat Protect E, then you can see there is just a very, very small variation. And more or less the same thing with the diclofenac, you know, the same release profile. Simple to use, nothing to add, you know, for some of you working with metacrylates, when you prepare it on your own, it's sometimes consuming and a bit boring. So in this case, you can apply it as every other coating system. In some cases, you need a subcoat. This is not a magic thing. This is a regular HPMC coating just to avoid any direct contact of the tablet core and the enteric coating. Moisture protection. Again, aqueous systems, 17% solids. We love the 17. I don't know why it comes to this, that we love the 17, but we developed a couple of products and we found out that 17, it's good. And now we identified that we love 17. So this is something I would recommend. And for HPMC-based coating with some addition, like polydextrose or lactose, 17% is a good recommendation. Maybe one word to solid content. There are now some people in the market telling you, oh, we have solid content, 25%, 30%. I even heard 35%. This may be true that somebody has such a thing. But when you look from the practical standpoint, and this is not your lab equipment, this is the production equipment, and you apply such a weight gain and such a solid content, then you have to guarantee that you have a statistically homogeneous process. So every tablet should be able to get the same amount of spray. And when you apply 35% weight, 35% solid content, I doubt that it works, but let's estimate it works. How far you want to move the tablets, you know, what is the drum speed to make sure that this process is homogeneous. This is just one example. These are things, in practice, they are not working. They are physical borders, and these borders are dictated by the equipment. So as long as we are working with these pens, with perforated pens, and then we spray, even with nice Schlick guns and everything, so we cannot work against the physics. So keep that in mind. So we personally believe 20% is something good. When you do everything right, maybe in single cases up to 25. But above that, Okay, so when we look at the performance, you know, typical coating formulations based on HPMC, like our VivaCoat A, based on PVA, like our VivaCoat M Neo, or the VivaCoat Protect W. When you look now at the moisture vapor transmission rate, what is it? This is the amount of water penetrating in a certain time to a definite square centimeters or whatever. So the less are penetrating, the better it is. What you can see, HPMC is probably not such a good idea for moisture protection. PVA is much better, and I tell you, in most of the cases, enough. In most of the cases, enough. And this is another thing. You do not need always the max. You need the best for you. And in most of the cases, PVA protection regarding water, it's good enough. And when you need really a maximum, then you can go to VivaCoat Protect W. Taste masking. So taste masking, we tested this, is another, now we have 15% solids, sorry, no 17, and roughly 4% weight gain. And what about the taste masking? When you take a bitter substance, you make a tablet, and then you put the tablet under the tongue. And you measure the time until the people say, oh. So this is the experiment. So very simple, you can do it, you don't even need a lab, you can do it in the office, we can do it here. It's very simple, but effective and reproducible. You need just a couple of people, because normally you do not have to touch the tablet, they should wait, but some people are a little bit, nervous, and then they move it, and then it's getting faster. So you need 5, 6, 7 people, and then it's fine. Good. What we have done, we did these bitter tablet cores, and then we applied different weight gains, starting from 3%, 4%, 5%, 6%. What you can see here, that 4% is enough. So the rest, it's good, but normally nobody needs that. Again, the comparison to standard HPMC and PVA-based coating. We measured the time. You see HPMC, it's less than a minute. PVA, but it's not significant. It's a little bit better. But you can see here with the Protect T, makes really a massive difference. Last thing, and this is really something, let's say, exotic, when it really comes to the fact that you want to protect, for example, your API, or you use a natural color. And natural colors are, in a lot of cases, sensitive to UV light. Then a top coat of VivaCoat Protect U could be an idea. It's a clear top coat, and just to give you an idea how it works, this is a natural blue. And when you expose this tablet 6 weeks under the daylight lamp, then you see these fading out. And when you apply some VivaCoat Protect U, you can still see some fading out, but slower. So we cannot stop it, or you cannot stop it with that, but you can slow down the process. And there's a pharma grade, and there's a food grade as well as available. Here, the solid content is low because it's a clear with a little pigment inside. There's some kind of magic. One recommendation regarding the solid content, when you want to have a high gloss, it's a good idea to reduce the solid content a little bit. In general, doesn't matter which coating you are using. So higher solid content always causes some problems with gloss. So weight gain just 1%, so it's very thin. And here are the comparison, the curves. This is with VivaCoat Protect U on top, the degradation, and this is without. And we do this with a natural yellow and a natural blue. It's nearly the same effect, but it's exotic. This is a paradise bird you probably never touch. That's it. So thank you very much for your attention. I hope it was not too boring. So any questions regarding coating to the products or in general, even to competitive products? I spent more than 20 years now in the coating industry and 12 years with JRS. And before I was somewhere else. A company you probably know perfectly. So for that reason, you can ask me anything to get a different view. One topic, for example, where I have a different view, it's about PVA and scuffing. You know scuffing? Maybe you don't know the word, but you have seen for sure the effect. When you have a PVA-based coating, for example, white, and you apply this in big scale, important is big scale. Lab, you will not see it. Big scale, more than 60, 90 kg minimum. The bigger the scale, the more is the scuffing effect. You see then, after the coating process, some gray strikes or spots on the tablets. So what is the reason for that? Anybody has an idea? So when you see this and you ask somebody, they tell you, oh, this is about the titanium dioxide. Because the titanium dioxide is so abrasive and it takes off the metal from the drum. Half of the truth. The full truth is that PVA polymer creates a very, let's say, smooth and slippery surface. You can easily see that when you look at the tablet bed, when the drum is running, and the size of the tablet bed. HPMC-based coating is maybe that, PVA-based coating is that. So the transportation, it's much less. When you do it in small scale, nothing. When you do it in big scale, this tablet bed, pressure from above. And then the tablets, in direct contact with the drum, save the pressure from above, and because they are so slippery, they are not moving. And the drum is scratching. So this is one of the side effects of PVA coatings, only in big scale. Only in big scale, you should be aware of that. There's one way out. I know this, hundreds of companies are using this. It is not GMP. They spray the drum in advance. With the risk of peeling off. This is just one example. With the VivaCoat Free, you will not see the scuffing, even not with our HPMC-based coating. But with our PVA coating, it's the same thing. So we cannot work against this. Okay, good. If there are no questions, I think the break now. So thank you very much. It was a pleasure talking to you, and enjoy the rest of the event. There is? Maybe you can.
I guess it's just out of curiosity, but is there a possibility of VivaCoat protect also the API from the UV effects?
Yes, but there are no studies. You know, because this is, I got this question already a couple of times. You have to test this with your specific API and in your tablet formulation. We did test something like a general test. So we applied some natural colors into the tablet core. We mixed these natural colors in the tablet core, and then we did the protective coating, and then we measured this. So these are initial data, but it's not saying that it works with your API. I don't know how sensitive it is. So maybe it is a help, maybe not. By the way, another interesting thing, We have this with the VivaCode Free as well. When you remove the titanium dioxide and your API is UV light sensitive, and you do just a replacement with calcium carbonate or magnesium carbonate, you will lose this effect. So the UV light is hitting on your API. It works better with the VivaCode Free. So we saw this even in customer projects. So try it out. This is the only thing I can tell. In theory, yes, but there is no guarantee, and there are no data with 20 different APIs. We didn't do this.
Thank you.
Okay, break now.
Pessoal, só um recado rápido aqui antes do café. Tem uma lista de presença que a gente passou no início, né? Não deu tempo todo mundo assinar, porque a gente queria começar logo. Eu não sei se alguém ainda não assinou, mas ainda não, né? Várias pessoas. A gente vai passar novamente, vou pedir para vocês colocarem o nome, porque depois a gente vai enviar um certificado de participação, então a gente precisa da confirmação aqui da presença de vocês. Não. Na volta do coffee break a gente já entrega. Ou agora já. Tá. A gente também tem um material para entregar para vocês. Enquanto vai passando a lista, a gente vai entregando para vocês agora já. Vamos todo mundo, a gente já vai dividir, já vai entregar mais rápido.
So, ladies and gentlemen, release the seatbelt and relax. So nothing special, nothing stormy, nothing we have to react immediately, no unknown territory, so just regular things you can rely on and you can relax. It's not complicated at all. For the next couple of minutes, no pharma, but Nutra. So what do we offer for nutraceutical applications? First of all, one of our most selling product in the Nutra area is this one, VivaCode Seal. What is the magic in VivaCode Seal? Is it the composition? No. Is it the polymer we are using? No. The polymer is a very old thing. It is shellac, used in the industry since 100 years. So what is then the innovation? What is the specific? The fundamental, let's say, new thing is that we supply this coating formulation based on shellac, not in a solution, but in powder. And you can apply it on an aqueous base. No need for organic solvents. And this is in some of the countries on this planet, it's getting more and more important because restrictions are increasing. You cannot use organic solvents anymore without having a specific device to recover this, and this is expensive. So that's why aqueous is great, and you can use it in the same way as the other ready-to-use coating. Add it to water, stir it, use it. So, VivaCode Seal. We talked about the concept separate functionality from pigmentation. Even here, in nutraceutical applications, this is a clear coat. And depending on the weight gain, you can change the functionality of the coat. So when you just apply 1%, you may have a glossy appearance, you may have a smooth surface. When you apply 1% more, you get taste masking, then you get moisture protection, then you get even resistance against gastric fluid. So the big advantage is one product, one formulation, and you decide just by the weight gain about the functionality. In reality, most of our customers are using the VivaCode Seal for nutraceutical products as the final coat. For those, they want to make these natural tablet visible. In some cases, these plant extract and other ingredients are not looking so homogeneous. So the tablets are getting spotty, getting grayish, having gray spots or red spots. Some companies hate this. Some companies love this, because that gives them a very natural appearance. But it's your decision. When you love it, this natural appearance, then apply this as a clear top coat, and everybody can enjoy the nature of the spots. And if you don't like, you apply the same thing, and then an HPMC-based or whatever top coat, and the color you like, you can cover everything, and you have a smooth coating surface. Up to you. But this is in Europe, it's a very common product to use to isolate these nutraceutical tablets, and in most of the cases to get rid of the moisture sensitivity of the plant extracts. A lot of plant extracts are moisture sensitive. And the tablet itself, the hardness, the friability, it's in some cases not that good. So to have a proper isolation and the moisture protection, you can use this VivaCode Seal. It's an aqueous system. Again, my lovely 17. Tablet bed temperature is a little bit higher. The only thing which makes the difference to all the other coatings, you need warm water. But you dilute. This is not a suspension. With this formulation, you dilute the shellac in water, and there's no pH you have to adjust. You dilute it, and this diluted coating stays stable. You can keep the rest for 2 weeks in a shelf, and then you do not have to even stir it again. It's still diluted. So only for this. Please do not this with the others. Only for this. So the weight gain, as I said, depending on the functionality you want to have. Experience-based, what our clients are doing is something like 1 to 2%, 1.5 is in most cases enough. So it's not a big thing. It's not time-consuming, and it's very, very efficient, and you can solve a couple of problems with one thing. So when you look at the taste masking, and again, the comparison to a standard HPMC-based coating, again, our VivaCode A, this would be our VivaCode M Neo, and then the seal, you can see it takes much longer to get the bitter taste. It's the same experiment you can do in the office, put the people this thing under the tongue and then measure the time. So it's much more effective. So water absorption, when you apply 4% weight gain, then compared to the PVA is much better. And you remember PVA coatings is a relatively good moisture barrier. And even with half of that, roughly 2%, you are better than 4% PVA. And this is something significant. And this is why nutraceutical companies love to use it, because you just have to apply a little bit. You are fast, you are more or less cheap, and you are efficient. And the surface, it's for those of you who know shellac as a polymer, the surface is nearly perfect. So water absorption, depending on the weight gain, so you can see that it's getting less, and even 3%, so it's more than enough. Simple as that. Simple product, straightforward, and again, just to try out. Thank you. So the last one, it's already open. So we stay. Question. Sorry. Thank you for reminding me. Can somebody supply a mic? Yeah, I have to wake up my colleagues as well a bit, so not only this.
A quick question. How much time of steering is needed for this product? Is the same or for the others? Like 40 minutes?
To get it diluted.
Yeah, exactly.
Yeah, it's the same equipment. Mm-hmm. So it's a propeller stirrer, and you apply these vortex, and you add the VivaCode seal, and then you let it run. To be on the safe side, I would do it, let's say, for 1.5 to 2 hours in this case. The reason is to make sure that every particle is getting really diluted. If not, then it stays like that, and then you have to stir when you use it again. But when it's once diluted, it stays like this. So normally for all the other products, 45 minutes stirring, as you know from competitive products, same thing. But here I would recommend to do it a little bit longer.
Okay. Thank you.
And it's a natural product. You have, of course, some batch-to-batch variations, and you cannot measure it exactly by seconds or whatever. So sometimes it takes maybe 1 hour, sometimes it takes 1 hour 15, but this is based on a natural product. And it's for nutraceutical, it's not for pharmaceutical use.
Thank you.
Anything else?
It's okay.
Good. Last thing for today from my side. Very short, again, very easy. If you remember the trends of coating in the pharmaceutical industry, chemical, semi-chemical, natural. We are now at the very end, and we are getting very, very natural. What is the benefit? Is it a gorgeous coating with a gorgeous functionality? No. Is there any benefit regarding that it's more effective or a shorter coating process compared to PVA-based or HPMC-based? No. Is it cheaper? No. What is then the benefit? The benefit, it is natural. So what I'm telling you now, it's really, let's say, for those companies, they want to use in their marketing story these natural coating. When you have already a very natural product, and the focus and the main selling argument is as natural as possible, this is the coating. But when you are happy with a nice PVA-based, nice HPMC-based, and there is no need, then don't touch this. Okay, the surface is very smooth, it's very nice, but it's just a clear coat. Again, the main benefit, it's a marketing benefit, it's natural. So it's based on alginates, and we have, so this is the composition, is the alginate and it's a plasticizer. So you remember this plant-based plasticizer, this is exactly what it is. The source is the alginate. We have a company we bought in the north of France a couple of years ago, and they are harvesting these algae in the ocean. And then there is some kind of extraction of the alginates, and then we make a polymer out of it, even for other applications, and we use a specific grade for preparing a ready-to-use coating. So it is label-friendly, so no allergens. So for all of you, as I said, they want to have something really without anything. You cannot take a single thing out that it doesn't work. This is just a polymer and a little bit of the plasticizer. This is a minimalistic product. So weight gain, we recommend 1.5% in most of the cases is enough. You have no functionality, no moisture protection, no enteric, nothing, no coloration, but a very sexy surface. So simple as that. And you can tell this natural story. So here are some recommendations about how to use. I do not want to go into detail now in the late afternoon. Just to summarize, it's a plant-based polymer and a plant-based plasticizer. So it's not a chemical glycerine, it's a plant-based glycerine. Is there a difference in the performance? No. Is there a difference in labeling? Yes. And it supports organic certification. So this is different from country to country. There's US organic, there is European organic. This is, when you look at detail, something completely different. There's probably some Brazilian organic. So it goes into that way. It is not a guarantee that in every case it works for the organic certification, but it's a product supporting this way of organic. So last time, thank you. And last time, the opportunity to raise a question. But it's so simple that it would surprise me when there's any question. Just try it out. Interesting is when you coat tablets and you put it somewhere in a bag or container, you put your hands in. It's interesting. It's a feeling of the surface, and it gives an impression of how much nature there is contained. So this is, I was impressed about this. And we did that once at the exposition, just to attract people a little bit. Come on, touch it, and then go, oh. So this is, yeah. Good, thank you.
So this is the last session of the day, and I want to thank you all for your patience and your attention, but I would ask if you could really, I wouldn't say pay attention, but more than that, receive this with an open mind, and please think of this as a rough guideline, if you want. So as a new framework to formulate stuff, because it's a new product. It's something we're launching this year. It's something that we've been developing for over 10 years in the company. We have been reformulating and fine-tuning it. Of course, none of those 10 years have been straightforward, development and research. Is a lot of decision-making involved, and a lot of long times, and a lot of other things, but it's taking a long time, and we're really proud of it. We started a small trial last year with a number of countries and regions, and we tried to see how it works, and we put it out there for those to try and get some feedback and see if it works or not, or if people really see a use and a value in this product. And it turns out that quite some people did, to the extent to which we are now expanding capacity, because we already, with this pilot launch, sort of like, we outsell ourselves. So It's a good success, but we want to make it much bigger. And there is a lot of potential for it. And we have a rough idea on what we can do, and we do have some things in mind, but there is probably a lot we're missing, and that's where, well, you play an important part here by just thinking along and playing with the product as well. So anyway, without further ado, I'm just going to talk a bit about what ProSolve 730 is and what does it do. So if you have any question, please ask it any time, and if not, think along, because I would love to answer some questions, and also maybe not questions, but ideas. I think it's going to be very valuable for us, at least. So 730 is our answer to how should we formulate lipids in the future. And when I first joined the company, I was put in front of this and say, well, this is what you're going to be together with SMCC and EasyTab and some of the other high functionality stuff. This is going to be your product for the year. We want to launch this thing, and we need to make it successful. And being the skeptical person, if you wish, coming from an R&D background, I was just posing a lot of questions. Yeah, does this work? What is this? What is that? And so I was a bit resistant in the beginning, because I've tried some stuff like this before, and it never worked. And because I put my hands in the lab on that, and I was trying to tablet that, and it never actually worked that well. I was skeptical, but I was fully convinced when I saw it and what I was able to try it. So the idea is, simply put, and I'm going to show it to you, but before we go any further, the idea is we load oil into a powder, and then we tablet that, and that's it. And we have a tablet that includes oil. So how do we do that, and why? And there's a number of things we can do with this particular product. Is this working? All right. So what is it? And typically we do it the other way around. So if I present this to a more of a sales environment, I'll say, this is what you can do. This is, the end goal of this product. But because everyone here is more or less involved in a technical field, I want to explain what it is first, and then we'll just think of what we can do with that or not. So it's a co-processed high-functionality excipient, as I defined before, and it's made out of MCC, silica, and copovidone, pretty much tying the whole thing together. That's it. It looks like this. Into the SEM, I don't know if you can look at it. It looks a bit gray here, but basically you see a bunch of fibers. That's the MCC. That will be coated, of course, with some silica, and also you're going to have these big balls of silica that are the ones doing the whole thing. And copovidone is there to pretty much keep the whole system together as a particle. So that's the idea. And the purpose is, as I say, well, this is beautifully put, to provide solution to the challenges of drug delivery of lipids and the associated solubility challenges, eventually improving bioavailability and the therapeutic performance. But basically, what we do is we just take oil and load it onto this ProSolve, and we tablet that. And why? So why did we look into something like this? Is there a need in the industry for that? It turns out it is, both, by the way, in the nutra and in the pharma field. So this is not a nutra or a pharma thing. This is a general thing. This is how pharma looks right now. So currently, we have roughly 60% of molecules that are relatively water-soluble. And then you have a bunch of others that are posing some challenges. So they are either non-water soluble or slightly resistant or not so water soluble. This is, however, how it looks like in the future. So it's quite bleak. We just have a lot of molecules that are not water soluble, and we can close our eyes to this, or we can assume that is how it's going to be. So of course you have the biologicals on one hand, but then if we look at the small molecule market, this is how it looks like. So we have a lot of things out there that we cannot simply put in water. And we need a number of different strategies for that. And there is something out there. I mean, people is formulating these things already. But we're just going to provide with a different solution, or at least a different tool for you guys to take a look at that. So 90% in the pipeline is not going to be water soluble. The alternatives for formulating the BCS class 2 and class 4 are being investigated. There's a number of solutions there. I'm going to go through those later. And then we need to have in-house solutions. That's what we want. Of course, you have an API that you cannot dissolve, and then you just send it somewhere, and they might think of a solution for that. That solution might be expensive, take some time, but you cannot really do it in the way that you used to do, and maybe your expertise is in granulation, tableting, or something like that. And most of those things you cannot even do in-house anymore, and you have to externalize and subcontract someone and get the whole thing done. And it takes a lot of time and effort and money. So we base the functionality, we explain more or less how this all works in 4 pillars. We decided to name them. First one being the oil resorption, so that's pretty much what it does, and then DC, of course. The main goal is everything that you can formulate, maybe not everything, but some of the things that you typically will formulate in a soft gel, you can now put into a tablet. So you can do that in-house instead of externalizing a soft gel, which is expensive. Not everyone can do it. They break, and it's a bit not so convenient. You can enhance the dissolution of an API. We're going to go over that a bit later. This is not directly a value proposition of the product itself, but the product is really enhancing or, let's say, facilitating that you can actually do that with some other stuff. And eventually you can also, why not, build some modified release profiles. So the first one is oil adsorption. And we have a couple of videos, but before I'm going to explain what you're going to see. And the idea is that you can take up to 25% of its own weight, so 4-to-1 ratio, converting oil into powder. So basically you can load 20 grams of oil into 80 grams of powder, and then you blend it, you mix it, and that's it. You can load even more. So the question, the first question we get is like, okay, is that enough? People try to challenge that. We've tried. You can go below this 25 or this 4-1, you can go, no problem. You can tablet that, no problem. You don't have any leakage. Everything works well. You might be able, depending on your oil, depending on your API, you could go higher than that, but we cannot guarantee it, but can be that is good for you. If you're looking into tablets, if you just want to encapsulate this powder, for example, you can go higher. I mean, it's going to take even more than that, but we are not saying it's going to be tabletable. And it's funny because, I mean, I have from the lab a lot of funny experiences with this thing. If you take the tablets in your hand, we did not bring any, but if you take them right after they are loaded, they dry your hands because they take the grease of your fingers really fast, and then you really feel like, you know, you have dry hands really fast. So the product is still taking moisture, taking fat, but of course, then the tablet will be a problem. So this is how it works. Thanks, Val. So this is a warring blender, just a kitchen thing. It's just very, very simple for the purpose showing. I hope you can see the blue thing. We took Sudan Blue 2, which is a colorant that is lipophilic, and we put it in castor oil. So we just diluted a colorant that is oil soluble in this oil, and then you wait for 5 or 10 minutes. This is an accelerated video. You'll see the cuts, and then eventually the whole powder bed turns blue. And of course, you can validate how long it takes and whatever. But the thing is that it really takes the oil. And after doing that, you can do whatever you want with that. So you can further process it. You can tablet it. You can just encapsulate it. You can do whatever you want. So if we see the next video, you can see that this is after loading. This is still a powder that is freely flowing. It is actually flowing better because you're increasing the density. So it just goes much better than it did before. This is after 10 minutes at the highest here. But again, we're looking at the kitchen thing. The first question that we typically get is, all right, I do not have any highs here. Is a free-falling tumbler, a V-blender, a tubular blender, something like that, will it work? The answer is yes, it will most likely work. It's going to take longer than 10 minutes, but you can make it work. So we still don't know, but we think it can. So again, this is more or less the limit. You can or you could further load it, but we cannot guarantee it. You have to try yourself. And this is just basically how a tablet looks like. So you kind of like have to trust the image, but you can tablet it and they look very, very well. They look even shiny. You can coat them afterwards. We've done that as well. I have not included that in the slides because we just did it actually, but we're actively working with that in the last, I spent the whole August just working with this. Yeah. Again, the same proof of concept. Is the co-processing bringing something, or is it just a fancy way of selling two products in one? No, it really is bringing something. So again, we compare what will be the dry blend of the simple excipients with the oil, and we compare that to 730, and this is a compactability curve, and you see, well, pretty much at 5 or at 4, at the lower compaction force, you cannot even tablet the dry blend anymore, where you can, from already 4 or 3.5 kilonewton and all the way up to 15 and probably even longer, you can tablet the loaded 730, no problem. So of course the first application that we thought of is, all right, so we have a lot of soft gels that we could translate into a tablet just like that. Not all of them, of course. I mean, we cannot load, we said, no more than 25. So fish oil is, for example, not a direct application of that. But there's many things, many vitamins, many stuff that we could just translate into that. Just looking at the neutral perspective, of course, pharma is a different question. And we ask around, and everyone that is doing soft gel, maybe not everyone, but 90% of our customers, they're not doing that themselves because they do not have capabilities to do that. They kind of like send it away, and then a company is manufacturing that for them and just sending them back. So it's not that in-house. They also don't have the knowledge. There are not really a lot of companies doing that, at least not in Europe. And then the thing is, by doing this in-house, you have a lot of control over what you're doing. And you can do it, and you can try different things, and just a tableting process that you are experienced with. So it really enables the direct compaction tableting for lipids in your lab. Which all the costs and time savings that will bring eventually gelatin-free formulations as well, and you become a really fast emulsion in a dissolution medium. So basically what we do is, because we put the powder in, we put the oil in the powder, and then when you put it in water, and you're going to see a video right now, you see that it creates a mist of droplets when the oil releases into the medium. So that is... it's not only that you put the oil, but also that the way that it liberates and frees in the medium is very good. So we came with the first case study. You're going to see a couple of them. And we just bought coenzyme Q10 formulated already in the soft gel. And what we did was just break those, take the oil out, load it into 730, and then tablet it. And this is pretty much the tablet equivalent of a 100 milligram CoQ10 formulator. And it worked from the, say, galenic perspective, so you could tablet that, fine. But then the question was, all right, so how does this look? So again, 730 was the enabler of going from here to here, and then we just brought it into a beaker with water that will be eventually dissolution medium. Well, could you just click on the thingy? Yeah, thanks. So on the left-hand side is the capsule, on the right-hand side is 730, and it really breaks apart and creates this really fine mist. What you see is very attractive, but I also have to say it's not only, so what you see here is a mixture of oil and the particles, because they are like non-soluble particles, right? So you're gonna have a mixture of those. But in the end, you see how very little time it takes. It creates this mist, whether the soft gel just sits in the bottom for quite some time. Of course, this is not like a proper pharmacopoeia test, but still reflects very well what we are trying to show here. So the video is going to run still for a couple of seconds, and then we're going to try to steer it so you can see. You can roughly see the tablet, but the tablet will also disappear in a bit. Yeah, so and now we move it again, and there you go. So that is the main pitch for the product, and everything that is from here on is, I would not call it the speculation, but things that we're trying out, and this is not something that we alone have to do, but also things that we expect the customers to take a look at and come back with feedback to us. So it's very exciting. And of course, there is a number of arguments for this and for the importance of this in the pharma field. And I also don't want to bore everyone with a very pharmaceutical topic. But I think it's important to think about the bioavailability of most drugs, right? So we have a lot of things that are not so easy to get into our blood. And one of the things when it comes to to pharma right now is the poorly soluble APIs. That's class 2, class 4. So we have a number of things that cannot be solubilized, and also a number of things that cannot really go through the gut, right? So you have typically 3 problems. The first one is the solubility. If you don't get anything soluble, you cannot really get it into your blood. The second one is the permeability. So depending on the transport system or not, you need to get that solubilized thing through. And the third one that is unavoidable and is just the way we are designed, when we're talking oral, is the first pass effect. So everything that goes through our gut will go first through our liver. That will, it will metabolize at least part of what we're getting. There is also a first metabolism, a local metabolism step, but we can kind of like forget about it. And whatever remains is the bioavailability. Most of you know about these things, so I'm not gonna really spend a lot of time here. This is very, very basic. And then, you know, according to that, according to the solubility and according to the permeability, you typically have 4 classes. You don't have to really worry about the first and the third, because the first and the third are really high soluble, and we want to concentrate about those 2, particularly about the class 2, because, you know, when you think about it, it has a low solubility but a high permeability, which means that the bottleneck right here is to get it dissolved. The moment you get it dissolved, it's going to transport through the gut and then into your blood after the first pass effect, whatever, you can adjust the dose, but the bottleneck here is this low solubility. Once you get rid of that, it'll work. So the dissolution is the limitation step. We cannot really change the solubility of the API. We're not doing anything with that. But we can change the rate at which it dissolves, and we can do something with that. We can play something. Yeah? And of course, if you enhance the dissolution of it, you can improve availability. So you can lower the dose, and you can improve the drug efficacy, and you can also improve the speed of onset, and you can eventually get a better safety profile. And everything that we do here is going to add up to a better therapy. And it's going to contribute not only into making this thing work, but into making it work better. So also for you eventually is going to be a good, it's not an excuse, but it's a good argument to say why my product is better than others, because I'm just improving so many things. But yeah, so again, what you need to enhance solubility, you have a number of alternatives, and you can do a number of things. And we have here Process 30 as a standalone alternative, but it's not exactly true, or it doesn't really have to be exactly true, because you can combine that with whatever is already existing. So the first one that you can do is, decrease the particle size. So you basically just take the particles and you chunk them as much as you can, so that by doing that, you increase the surface area, and you will be able to get more of a contact with the medium, and eventually you're going to be able to dissolve the API much better. So you do that by jet milling, high pressure homogenization, or maybe doing a bottom-up controlled crystallization, which takes some energy, time. You can make a lot of mistakes, and it's not that easy. So you can maintain a reservoir of the dissolved drug, you can build nanosuspensions, fine. But then the challenges are the cost. The challenges are that you need to keep the equilibrium unchanged, that you might have some other polyform forming during the processes, and that still the drug is in solid state, so you can get, again, crystals forming and bottoming up and undoing everything that you're doing. So it's not that straightforward. It plays a role, and that's why I say that everything has to be combined in the end. The second one is working with amorphous or metastable polymers. So of course you have a crystalline structure. If you manage to turn that into an amorphous structure, it's going to be more soluble. And that is basically the strategy. Yeah? So you try to do that because you know that this one will dissolve faster than this one, and then you need to do it in some way, and you can spray dry that, and you can do some hot melt extrusion with that. You can do a number of things. But then it has problems. It's, again, very costly and very complex, and the yield is probably not best, and you're not changing the equilibrium. And in time, of course, everything will revert to crystal. And still, you need to dissolve it. So, again, not perfect. The next one is doing salt forms, co-crystals, cyclodextrins, doing blow drugs. Basically, we're getting those bricks, being that API, and then we do things. We make them salt, we make them a co-crystal, we make them a hydrate. So you can do things to enhance the solubility of the API, but the main problem here is that, well, not only is costly and complex, but also you have a lengthy regulatory pathway, so you need to declare safety on all of those things that you're doing with your API, and it's not that straightforward. Again, you need to dissolve it, so end of the road is the same for everything. And one of the, most well-known and the one that is probably the go-to way of working with lipids is the soft gels, or not only the soft gels, but those systems that are self-emulsifying drug delivery systems. So these METs, a soft gel capsule, basically it includes the drug, it includes an oil, a surfactant, a number of things. And you can do a lot, you can include a lot of things here, but very few people have the capability of doing that, and they are very expensive, and they break, and it poses some problems. The handling is a problem. The microemulsion often needs a surfactant to work, and it has to be formulated as a soft gel or as a liquid, and yeah, quite frankly, it's not that cool to work with liquids in a lab, particularly not with lipids. And then we have 730, which again is probably for most not a standalone solution, but you have to combine it with something else, but it could work. And this is what we're saying. We have a mesoporous silica particle that, well, this is kind of like the pore range for those working maybe with nanocrystals or something like that. Might be of interest, might be fitting or not. This is the really surface area that can get up to. The idea is that those pores will host these polysoluble compounds, being that oil, or maybe you can do a solvent deposition and load up the particles and the drug inside. And, well, this is more of the regulatory thing. We're not creating a new compound, so it's a co-processed. And the regulatory pathway, you have to register themselves as separately, the same way you would do a coating, so by the individual components, and because we're not creating any new chemical entity. And of course, I need to talk about the advantages. It is less costly than particle size reduction. It brings a fast emulsion into the solution medium. You've seen that. You can drug load in oil or an amorphous. It is simpler and probably faster and with a better yield than doing some spray dot dispersion or a hot melt extrusion. You can use an inert carrier, so you can use different kinds of oil to solubilize your API, and you can do it in-house. You don't have to really externalize it, and it's much easier when you load it into a powder and you work with a powder instead of working with oil. There is not really a lot of regulatory hurdle as creating a co-crystal or a new salt, because you're not really altering the API or registering any other new excipient. And you could eventually work with gelatin-free if that's what you want to claim in your typically nutraceutical. And we have, again, case studies, which I'm really happy and proud of. So we got loratadine. Loratadine is a second-generation antisemitic that is low dose, typically ODC. BCA class through, it's not really water-soluble, but it has a good lipid solubility of 85 milligrams per milliliter in castor oil. So we use that. And the reason why is not only because of the properties, but also because we were able to compare that to one of many OTC formulations. So we have many over-the-counter formulations, and we wanted to check how good we perform against those. And we have x-axis this time. This is your dissolution profile, percentage release in a open one normal hydrochloric acid medium. And this is the commercial loratadine formulation. So this is basically what you get when you take the ODC and you do the dissolution study. Good, and this is what you get if you put this loratadine in castor oil and you encapsulate that. So we kind of like did the same thing ourselves. We're not that good as the commercial one, but after 20 minutes, we were mostly there. And then we did the same thing using 730, and we saw that we were much, much faster into getting to the 100% label release. So just within 5 minutes, we were able to put pretty much all of the loratadine out there. This will, of course, translate to a much, much faster relief of symptoms in the patient when they take it, so you don't have to really wait. And then you can argue, yeah, all right, but Guillermo, this is done for maybe keeping the effect for longer. But you can also do that with, I'm going to explain how later. So you can adjust this dissolution as you wish, but you can go as fast as this. And this is also very interesting. This yellow-orange line is loratadine in ethanol loaded into 730. So basically, we have two routes here. You can take the loratadine, you can put it in oil, and then you can load that into the 730. Or you can put loratadine in ethanol, and then you can load it into the powder, and then you can evaporate the ethanol, and then you basically have the same thing. So you have the loratadine loaded into the powder. And the release is pretty much identical. And the last thing is the modified release. So modified release is, of course, a big topic. Everyone knows what it's about, and there is different strategies to work with that. And what we are saying here is that 730 might be just about another idea for you to work with. So you can do it in different ways. So as we explained, you take your API, you either bring it in oil and then you load it, or you put it into a solvent, and then through solvent depositions, you get it loaded. Direct compaction, you get your tablets, and that's it. So we took, again, loratadine, and we loaded in Lubritab, which is one of our excipients, and then we put it into 730. And this is kind of like what we got. This is the dissolution profile in red. But then we did not use any super disintegrant. So basically, we just put it, and of course, the tablet will take a bit longer to break apart and to partition into the water phase. And that's why you get a much, let's say diagonal, so like a lower release profile. If you put an SSG, you get it much faster. So you can do things with that. You can eventually use a coating on top of these. You can use different strategies. You can use different oils, because probably different oils have different partition coefficients, and they could release the API in water faster or slower. So this is, as a summary, basically what we get. I've talked about it, so those are the 4 pillars. The takeaway of today is you can tablet oil basically by using 730. You can simplify that. You can eliminate all of these softgel formulations. You can get a dissolution enhancement. You can work with different strategies to get that done. And you can also build extended release. So improved handling of oil or lipids, in-house tableting instead of softgel, improved bioavailability, and wider formulation options. Thank you for your attention. If you have any questions, I'm really happy to hear them. Sure. Thanks.
Quem quer? Quem é?
Eu gostaria de saber se existe algum estudo com o ômega 3, com esse produto, ele em comprimido, né?
No, we haven't, and I think it's, for us, out of scope, because the amounts that you need are typically very high, so the loadings are exceeding much more what you can actually get in this 25%, unless you're able to go to tablets that are like 1.5 grams or something, and they might work, or you want to take multiple tablets. So the short answer is yes. The long answer is yes, but do you really want to go that way? So we could do that. It's just a matter of tablet size and patient compliance and stuff like that. I think it's a bit, I mean, particularly looking at this kind of formulations is a bit too much. But also, let me tell you, I've been doing different things in the lab myself, and one of the goals, for example, is using in the CBD industry that is booming pretty much everywhere around the world. You can just load things that are not even oil, things that are like tar-like, you know, like really thick, pasty oil stuff, and you put it with 730, you apply highs here, and you get that distributed, and you tablet it, and it works wonderfully well with CBD, for example. I've been doing stuff in the lab with, so just last month I was working with a company that were providing samples, and they were, they were building systems with surfactants, oil, and some other products, and then you can load that directly, and actually it just works exactly the same as a soft gel. So it's basically the same concept, but you can just do it yourself, basically. Thanks for the question. Any other question or ideas? I'm also very happy to hear that. If you don't want to share anything, like right now, you can just approach me, get my card or something.
So, Sanchez, no disadvantage at all. This kind of mesoporous silica you presented, this material presents some holes and the nano range. Yeah. So probably, if you have this oil inside this tiny hole, you have maybe a nano-based system, drug delivery. I don't know. I was wondering,
It might be, yeah.
It might be. I guess because of your dissolution profile, it's so. Maybe only if you dissolve your API in an oil, you do not get these results. You need the mesoporous silica maybe to get this. Okay, probably I will ask you some samples, okay? Yes. And then we can compare with my nanolipid particles, okay? It will be interesting.
It's good. It really depends. I think it comes down. I've been having I have friends that also are doing postdoc right now, working with nanocrystals. And one of the things that they post me like, well, is it something really, what is the pore size? And the next question is, are we really able to load it into the pore or not? And this is an open question. This is the first thing we launched, so to speak. You can get the pores in different sizes. You can do something like that. This is very new for everyone, also for us. It might be that we're, in the future, we're able to offer something else regarding the pore size of the silica.
Yeah. And I was thinking about the drug nanocrystals also. You can also stabilize maybe the drug nanocrystals using this Prosolve 730. Yes. It will help maybe. As you said, it's not that easy to stabilize drug nanosuspension. But once you get it, it's okay. You can do it. However, if you improve this stability using the Prosolve, for BCS class 2 drugs, this is a break point. Maybe in the future you are presenting, the best ever, way to compound, to manufacturing the BCS class 2 drug substance. I can forecast, wonderful things using this. My brain's just, getting hot by now.
Right now my biggest fight is to get more capacity. So my internal fight is I'm completely confused about the product. I just need to push the management into.
And I think this is unique in the market because I have never heard about this again.
Yes. It's a good point. It's something I haven't stressed enough. So when I was first presented with this, I said, no, I work with this. There are some other companies working with this kind of things. And it's true, but it's not true. There are enough material out there that can take up lipids, but they're not directly compactable. And if you blend it with something else, as we proved before, it's also not working as well. So you need the co-process for it to actually shine. So I've tried formulations. Maybe I can go all the way back. I've tried formulations because I was doing that myself in my former company, trying to get it's going to take a long time, sorry. Trying to get these products that take up oil and mix them and formulate them in a way that I can make tablets out of them. But I was always landing here, or probably even here, not even getting tablets anymore, and I was very frustrated. So when I came into the company and they told me, like, this is what we have, it's not going to work, I've seen it before, it doesn't work. So for some people, it's completely new and it's fascinating. For the people that have a bit of experience in this field, they say like, no, I was promised that, I did not get it, and I'm not going to ever try again because I'm convinced everyone claims I can do it, but they cannot do it. Then I can tell you with fair enough confidence that we really can do it. I've also been doing different things. I've been working with we're just having a lot of ideas. So maybe you can take 730 and you can divide it in two, so to speak, and then one half you load with oil API, and the other half you load with a surfactant, I don't know, maybe a polyxamer or something that is waxy by nature, and it's a mess to blend with something. So you might even melt it, load it, and then you work with the powder. And then you have pretty much a ready-to-go product as well that you can mix with your API or with your oil powder. So there is a lot of possibilities for it. And we're just getting to know a bit more about it and trying new things. So it's very interesting.
I agree.
Yeah, so if you have a great idea, and again, this has to be right now because we're at the point in which we do not have a lot of product. We always have a small R&D sample. So, I mean, if you say, do you have 10 tons? I would say, like, come back in a couple of months, maybe we'll talk again. But if you're requesting like half a kilo or something to play in the lab, get your hands on, I think we have those. And I think it's very important that we get people also building pressure for us, that we are able to give the management signal like, hey, this is working, people really want this thing, and they are seeing good results with it. So reach out to Val anytime if you really have an idea, and if you have, I don't know, over a coffee maybe with Val, you can just pitch him this is what I'm trying to do with this, and you'll get a sample and you can let us know. So yeah, thanks a lot again for your patience. Thanks a lot for your your interaction today. It's been great. Very happy to be here and very happy to present all of those things. So again, thank you very much. And again, if you have any question right now or after, here for you. Thanks.